Okay, so so the end of the last lecture, I think we were looking at series, which for Jonathan's benefit are infinite sums. Okay. And you say a series converges if the partial sums converge. Yeah, so we've done that. We were just at this point. Okay, so remember yesterday we defined Cauchy sequences. So Cauchy sequences were satisfied for all epsilon greater than 0, or exists capital N in the natural numbers, such that for all little n bigger than big N, M n bigger than capital N, xm minus xn. So this means for all upside down A, this backwards E means there exists. That's set membership. Double stroke N is for set of natural numbers. So this is the definition of a Cauchy sequence. Okay, Cauchy sequences, it's kind of saying no matter how close you constrain the sequence to be, if you're far enough along, sooner or later the terms are all kind of that close to each other. And yesterday we showed that any Cauchy sequence converges. Any what was it? What was the? It was a bit more restricted than that, wasn't it? What was the condition? Oh no, that was fine. Yeah, every Cauchy sequence converges. If we want to prove whether or not a series converges, one way we could do that is to look at when the terms in a series are Cauchy sequences, when the sequence of partial sums of the series is a Cauchy sequence. So I think we're going to go through go through a few conditions for the convergence of series, okay, which will be useful. So what's this theorem saying? Well, I can both see. So suppose we've got a decreasing sequence of positive numbers, okay, real numbers. So AN is decreasing, it's bounded below by 0, and the claim is that the series sum minus 1 to the n, n is 1 to infinity. The claim is that that converges. Okay, and let me just. So what we're going to do is we're going to prove that this partial sums of this series form a Cauchy sequence, and then because we showed that Cauchy sequences converge, we'll know that this thing converges. So this is kind of intuitive, right? This is like something positive and something negative, something positive, something negative. Okay, and we've assumed that AN goes to 0. So what are the partial sums? Let's define S capital N is the sum from n is 0 to capital N of minus 1 to the power of n times AN. Okay, and we want to show that Sn is a Cauchy sequence. Okay, so for any of these proofs, we always start by saying let epsilon greater than 0. Okay, we want to find a capital N such that for big enough M and N bigger than N, this is true. So let's have a look at Sm minus S. n. Let me call that something different so we don't get. Just reading things about. So that's got an A there. Too many letters. Okay, we'll use P and Q. Okay. So let's have a look at SP minus SQ. Well, just from the definition, that's for some n is 0 to P minus 1 to the n an minus for some n is 0 to Q minus 1 to the n an. So if you like, we've got two sums, one's going up to P, one's going up to Q, we're taking the difference between the two. Okay, so it's going to be the terms that are left over, a lot of terms are going to cancel out, are going to be the terms from the minimum of P and Q plus 1 up to the maximum of P and Q. Okay, so this is the sum from n is min P, Q plus 1 up to max P, Q. Minus 1 to the n, a, n. And to make our life easier, let's just assume that Q is bigger than P. It's not going to make any difference. It's just relabeling things, right? Okay, so if we assume Q is bigger than P, then this is the sum from Qn is P plus 1 up to Q of what we had before. Okay, and we need to show that that this thing is bounded above by something. Okay, we need another bound for that. We know that an tends to naught as n goes to infinity, which means there exists some n in natural numbers such that for little n bigger than n, we have that a n minus naught is less than epsilon. Okay, so we can bound each term an by some epsilon. So now, you know, so one thing we could do is we could use the triangle inequality straight away here. Okay, if we use the triangle inequality on this sum, we get that this sum was less than the absolute value of a p plus 1 plus the absolute value of a p plus 2, absolute value of a p plus 3, etc., etc. And that's going to give us a bound which is related to epsilon times q minus p. Okay, but we want a bound, to prove that this is a Cauchy sequence, we want a bound that's only related to the minimum of the two, not related to the maximum. Okay, so we don't want our bound to be a function of q. So maybe rather than doing that, we can rewrite things a bit first. So we can write it as n is p plus 1 up to q of so do it like this. So let's so in general, write down this right. In general, P might be even, Q might be odd. We don't know which is going to be. So what we want to do is we want to group successive terms, right? We want to have a term which is an minus an plus 1, a term that's an plus 2 minus an plus 3, okay? Because we think the difference between successive terms is going to be small. But one of these might be even, one of them might be odd. So let's just so if P is even, then n would be odd. Okay. So and if P is odd, n is even. Okay. So let's suppose that the first n I'm in. Let's suppose that P is what did I say? Odd. Okay. So in the case in which P was even, if you like, we have an extra term on the front. Okay, suppose for the moment that Q is even. No, Q is odd. Okay, we want an even number of terms in the middle, so we want Q to be odd and P to be odd. So, okay, if P was even, then we would just have an extra term on the front. Okay, but because an is converging, we know that extra term. We can apply the triangle inequality and bound that extra term by epsilon, so that's not going to matter. Likewise, if Q was the wrong sign, we could put an extra term on the end and bound by epsilon. So this is certainly less than 2 epsilon plus the sum n is P plus 1 over 2. So this notation, what I've got there, funny brackets with a bottom but not a top, that means the integer part of. Okay, so this is like 2.5, this integer part of will give you 2.
What does that mean?
So this is 2, integer part of 0.1 is 0.
Oh, okay.
Okay.
Mm-hmm.
It's just some useful notation.
Mm-hmm.
Okay, so does that make sense? So we're just grouping successive terms together, okay, and we just have to worry a little bit about the endpoints, okay. But worst case scenario, we just have a few extra terms, but we can bound them. You want something?
No, keep going.
Okay. Such a pain, about it. Okay, so this is just triangle inequality. You know the triangle inequality, Jonathan. A plus B.
Yeah, I've just googled it. So.
Oh, okay. So you use it all the time. I hope I'm doing the right thing. Okay, and maybe I'm not taking the easiest route now. Maybe something slightly easier. Okay, so the proof in the book suggests that the next thing we need to do is to show that this whole sum is less than, so this thing is, the claim is this is less than a of the first term, okay, which was, what was it, p plus 1, a, p plus 1. So why is that the case? Well, we know, we were told an was decreasing. Okay, so certainly these things are all positive. Yeah, so if you like, we have so we've got something like a p plus 1 minus a p plus 2 plus a p plus 3 minus a p plus 4. Okay. And the claim is that this is all less, this whole thing is less or equal to a p plus 1.
So decreasing doesn't need to be strictly lessened.
What? Say that again?
If they're decreasing, wouldn't that be strictly lesser? AP plus 1.
Yeah, it doesn't matter. Go on, so how would you show that it's strictly less than AP plus 1?
Well, I don't know how to show, but
It's not going to make any difference,
no.
whether it's strictly or not
No,
strictly.
no.
The textbook says it's obvious, doesn't it?
Well,
so
I
it's
look
not
at the
negative.
textbook and it kind of makes sense, but proving's always the tricky bit.
Just need to, so this is, look, so we know that this is the biggest term here, so this is bigger than that, this is bigger than all of the positive terms. So it's certainly the case, I'm not sure if this is going to work, but this is strictly less than a p plus 1 minus a p plus 2 plus a p plus 1 minus a p plus 4. Okay, we just replaced all of the even terms. Is this going to work?
So can you just can you group just a couple of terms and kind of show, well, if AP plus 2 minus AP plus 1 is less than AP plus 1. Oh, hang on. Oh, that should be plus 3. The third term, AP plus 3.
No, so I was getting an upper bound, but
Sorry.
I don't think that's the way to do it. So this will do. So let's do this instead as so you know we know that that all of these terms are bounded by epsilon. You could also use that an is Cauchy, an converges, so it's Cauchy. So we know that this difference is less than epsilon. It's not going to give us what we need. Give me a second. Very easily from that, ak minus ak plus 1 is always not. I'm misreading something. So there, the answers are working with. So yeah, I think you must be grouping like this. Yeah, I'm stupid. I'm sorry, it's taken me too long. Suppose in total we have rather than having an even number of terms in our sequence, we have an odd number of terms in our sequence. Okay, then the last one is like so the last one would be a plus in that case. Okay, and the last one with what we started with was a q. Okay, so suppose we start with a plus in the sequence, we end with a plus in the sequence. Okay, and by throwing away terms at the start and end of the sequence, we can always make it look like that. Okay, then this is a p plus 1 minus brackets open a p plus 2 minus a p plus 3 minus. It is easy, isn't it?
Well, that's
I was being stupid. Yeah. This is what you were saying, wasn't it?
Yeah, I was trying to group the kind of them in pairs like that. Yeah.
Okay, so minus . Okay, so rather than before we were doing, I was kind of grouping like this implicitly, where we had some. So we always had plus terms. Now if we group like this, we always have minus terms, right? Because minus is giving a plus. AP plus 2 is strictly bigger than AP plus 3, so this is positive. So this is AP plus 1 minus something. Okay, so it's certainly less than AP plus 1. Okay, and we were told that all the A's were positive, right? So there's no so there's no difference between between this and okay. So at the moment, so we want this to be something of the form 2n plus 1, and that to be of the form 2n plus 2. Okay, so now we've got things with odd. We don't need the absolute values. And we just have this extra term, which is the first one, plus a b plus 1. Okay, so it's a slightly, that's a conservative upper bound. So do you see what we've done? So we had okay, so the difference in these partial sums was this thing. It was the sum of minus 1 to the n from p plus 1 up to q. We can throw away a few terms at the start of the sequence, start and end of a sequence, to make sure that the first one is even, okay, so that it's positive, and the last one is also even, so that it's positive. So possibly we might have to throw away 2 terms to do that. So that's why we get a 2 epsilon. And then we have all of these terms, and then we have the first term, which is bounded above by AP plus 1. Possibly we threw away an element, okay, but it's still going to be bounded above by AP plus 1. And then we have all of the other terms, okay, which are of the form A of an odd number minus A of an even number, okay. But because A is decreasing, this is bigger than that, these are all positive, okay. So this whole thing is negative. So minus A. No. Sorry. So we want to be subtracting. So we're subtracting an odd term, we're adding an even term, which is right. Yeah, this was right. Okay, so this is less than 2 epsilon plus AP plus 1, but AP plus 1 is also less than epsilon. Okay, so this is less than 3 epsilon. Get rid of the thing behind, as you can see. So here, the way I wrote it was kind of implicitly assuming that P was odd. Is it clear?
Okay. Yeah, kind of. I will just go through it again, yeah, later.
So we've just, the idea is what I wrote over there. We're grouping a negative term and a positive, so we're subtracting something. Okay, so then we get. Can I rub?
Yeah.
Longer than it should have done. Okay, so what have we shown? Well, we showed that that if an was a decreasing sequence converging to 0, okay, then the partial sums were Cauchy. Therefore, the series converges. Okay, so sums of this form always exist. Yes. So, for example, this sum here, this series here, will converge. So that's one useful condition for when a series will converge. This is another one, the comparison test. So there are loads of these different tests, and this textbook doesn't have all of them, but this is one useful one. So if we have, if Bn is a convergent series, okay, so we have some Bn and it's 0 to infinity. That thing exists, okay, and for all n, An is less or equal to Bn, okay, then the series sum n is 0 to infinity An also converges. Okay, so if the elements of some series are bounded in value by a convergent series, then you know your series will converge. Okay, and we're going to prove it the similar way. Let's see if we can do this a bit better. So again, we want to prove that the partial sums of AN is a Cauchy sequence. Okay, so if we define SP is sum n is naught to P AN. Okay, and we want to abound on SP minus SQ. Okay, well again, SP minus SQ, let's just assume for simplicity again that Q is bigger than P, doesn't make any difference. Okay, that's going to be sum from N is Q plus 1 up to P of AN. So what might we do next?
Use the triangle inequality.
So saying that this is less or equal to sum n is Q plus 1 to P absolute value of AN. Is that what you wanted? Yeah. Okay. And we know that each term absolute value of AN is less or equal to Bn. So this looks promising. N is Q plus 1 to P Bn. Okay, but this is, what's this thing we've got on the right hand side?
That's convergent series.
Yeah, but in particular, what's this? So it's the sum from Q plus 1 up to P of Bn.
It's that minus that.
Yeah, exactly. So it's the partial sums of the sequence Bn. Okay, so if we call this, so this is the sum n is naught to P of Bn minus sum n is naught to Q of Bn. Okay, but Bn is a convergent series, so its partial sums converge. So its partial sums are a Cauchy sequence. Okay, so there exists n in n such that for P, Q bigger than n, this thing is less than epsilon. And we're done. Okay, that was easy. Does that make sense?
The last one, the last step, yeah, this
From there
one,
to there.
yeah.
So what we had here was the sum from Q plus 1 up to P of Bn. So this is, if we look at this, are all the terms of Bn positive? Let me just check that. Bn positive real numbers. Okay, yeah. Oops. Yeah, so Bn's positive, so
So don't you say at the beginning, because we know that Bn converges, we can choose a P or
to Bn
such that it's less than epsilon. Isn't that just something you would say at the beginning?
So the way you do these proofs is normally you kind of start at the end and work backwards a bit. Okay, so normally kind of, or at least you start in the middle and then you work forward and then you work out what you need to stick in at the start. I was just worried about about that step. But okay, so sorry, let me go back to your point. Okay, so we had this sum from q plus 1 up to b of bn. All of the terms of bn are positive, so we can take the absolute value without any problems. If we look at this difference in sums, this is sum from 0 up to p minus the sum from 0 up to q. So all the terms from 0 up to q are going to cancel out, and we're just left with the terms from q plus 1 up to p. So these two things are the same. Okay, that's okay. But Bn is a convergent series. Okay, so if we define, I don't know, let's call it S hat. S hat p is the sum n is 0 to p of Bn. Okay, these are the partial sums of the series Bn. We know that S hat p tends to some limit L as p tends to infinity. Okay, we were told that Bn was a convergent series. So if this series converges, then it's a Cauchy series. Okay, any series is convergent series is Cauchy and vice versa. Okay, so S hat p. Okay, so for any epsilon greater than 0, okay, we started by saying that epsilon greater than 0, there exists some n in n such that for pq greater than n, S hat p minus S hat q is less than epsilon. Okay, so here what we've got here is just S hat p minus S hat q. Okay, so we can find an n such that it's less than our initial epsilon.
Can you just
Oh,
let
okay,
that
yes,
be?
okay.
Okay, thank you.
Okay, so that was it. Yeah, so they note that you can slightly weaken the assumption. You can weaken it to absolute value of an is less or equal to some constant times bn. Okay, because just scaling things isn't going to make a difference. You're going to end up with h epsilon at the end, but then you could have taken 1 over h times epsilon at the start, and then it goes through. And you have to be a bit careful that the assumption is that the absolute value of each a is less or equal to the corresponding b. It's not that the absolute value of the partial sums is less or equal to the sums of the original series. Yeah, so they have an example here. If you take, what do I say? AK is minus 1 to the k, and BK is 1 over k squared, then the absolute value of the sum k is 1 to n AK. Well, that's either going to be 1 or minus 1, right? So certainly,
You want.
yeah, it's It's 1, yeah. Yeah, but for series,
Yeah,
it's
yeah.
a bad thing, it's 1, yeah, you're right. And the sum k is 1 to n of bk. What's that? So the first term is 1 over 1 squared, the second term is 1 over 2 squared. Okay, so it's certainly greater or equal to 1. Okay, so here we have ak, we have the sum of the ak's up to n is less or equal to the sum of the bk's up to n. But we know that this series doesn't converge, right? So I'm not sure we've actually proven that that series doesn't converge. So the series is 1 plus minus 1, 1 plus 1 plus minus 1. What did we show? We showed previously that for any convergent series, the terms must be going to 0. Okay, so that doesn't fulfill that condition. You know, you might think that this is 0, this is 0, this is 0, so the whole thing must be 0. But you could equally rearrange this series, so you have 1 plus 1. Yeah, so take a so now we just kind of group things a bit differently. We've taken the first one at the start, and then we have a load of things in brackets after. So the same argument would imply that its limit was 1. Okay, so it doesn't make sense to start cancelling out terms. Like,
Yeah. So it's 1 or 0.
no, it doesn't have it doesn't exist. So if you look at the sequence of, so a series converges if its partial sums converge. Okay, and the partial sums of this thing are 1 minus 1, 1 minus 1. What are they? 1, 0, sorry, so we have 1, and then we have 1 plus minus 1, which is 0, and then we have 1 plus minus, yeah. Okay, so this series of partial sums of AK is going 1, 0, 1, 0, 1, 0, 1, 0, so it clearly doesn't converge, okay. So you can't start moving brackets around. Okay, and we won't go through that example. Another useful one is this ratio test. So this test is a bit difficult to use sometimes because you need it to find another convergent series. Okay. So the condition for this comparison test was that if there was a convergent series Bn, okay, then and absolute value of Am was always less than root of Bn, then we were okay. Whereas sometimes it's hard to find convergent series, so this one's easier to use. So this one says if we've got that lim n goes to infinity, a n plus 1 over a n equals, is it 1? Equals some limit L. Then the sequence converges if L is bigger than 1 and diverges if L is less than 1. The proof's very short. You were this one, Tina.
Sorry?
Well, you want to write things down? Just I can give you a minute.
Okay, yeah.
Are you? Do you need a minute to write things down?
No, I'm done.
No,
Yeah.
you're okay. Okay, sorry. So let's just go straight from the textbook for this. So this is the claim that if the ratio of successive terms tends to a limit that's bigger than 1, then the series is going to diverge. If it tends to a limit that's less than 1, then the series is going to converge. And the way you show it is if L is less than 1, then for small epsilon, you know, we only need things to be true for small epsilon, L plus epsilon is less than 1 as well. Okay, so yeah, so the absolute, we can introduce a load of terms. Shall I just write this big for you? Absolute value of an, well, that's equal to absolute value of an divided by an plus 1, but now we've introduced an extra term. So let's put an plus 1 up here. Okay, these two things cancel out, it's still equal to an. And let's put another term here. Okay, etc., etc. And we can carry this on up to some constant up to, we're going to have an plus capital N minus 1 divided by an plus capital N. Is this what the textbook's doing? No. Am I going the wrong direction?
No, it's right. It just needs to go to.
No, I'm getting the wrong direction. That's fine. It should be minuses. Doesn't make any difference.
So N is.
Okay, so these two terms cancel out, these two terms cancel out, you know, etc., etc. And we had up to an n was the last one. So these are getting these are getting smaller and smaller until we have a last one, which is an plus 2. So for some capital N, and then this is still an extra term that we've introduced, so we need to cancel it out, okay? So this thing here, well, these are successive ratios, because this series converges, okay, if we take for our epsilon, we know there exists n in n, so this is where we should have started, such that for all n bigger or equal to n, absolute value of an plus 1 divided by an minus L is less than epsilon. Okay, so I don't need that now. So this means that an plus 1 over an, this is our normal trig, is between L plus epsilon and L minus epsilon. So in particular, it's less than L plus epsilon. Okay, we don't care about the left-hand side. You know, we can. If epsilon is sufficiently small, this is going to be less than 1. Okay, remember, to prove convergence, it has to be true for all epsilon. Okay, but if you like, it's only difficult when epsilon is small. So if it's true for, you know, if SN's, remember we're trying to prove that this series, so we're trying to prove that SP, let's call it, which is n is 1, 2, 2, an. We're trying to prove that converges. Okay, so we're trying to prove that for all epsilon greater than 0, there exists n in n such that absolute value of S, so for all p bigger than n, absolute value of SP minus, let's call its limit m is less than epsilon. Okay, so this has to be true for all epsilon, but if it's true for, say, epsilon equals 2, then it's certainly true for epsilon equals 10. Okay, if this is always less than 2, then it's certainly always less than 10.
Mm-hmm.
So when we're trying to prove this, we can always take epsilon as small as we like. Okay, if it's easy to do it when epsilon is small, then we can certainly take epsilon to be small. Okay, so here what we're going to do is we're going to take epsilon sufficiently small that L, which we know is less than 1, plus epsilon is also less than 1. Okay, so if L is less than 1, then we can find an epsilon that's kind of also less than 1. So we could take epsilon as, I don't know, 1 minus L divided by 2 or something. So for any sufficiently small epsilon, this is going to be true. So we've got this ratio converging. Say that it's true for all n bigger than capital N. So we showed that each of these terms had to be less than L plus epsilon. Okay, that's what I just wrote down. So this is less than L plus epsilon times the number of terms now.
Mm-hmm.
How many terms are there here? Well, there's the first term starts with an n, the last term starts with a capital N plus 2, so there are n minus capital N minus 1. So, imagine this was 5 and this was 3, there would be 5, 4, 3 would be 3 terms, 5. So it's 5 minus 3 plus 1 terms. Okay, so n minus n plus 2 plus 1, which gives n minus capital N minus 1. So we've got L plus epsilon to the power of that, and then we've got the last term, which is a n plus 1. So what we've shown is that each term a n is less than some geometric series times an plus 1. What are we going to do with? Okay, well, these the a's are certainly bounded. Was that one of the assumptions? Surely must be. A and B a series of... So what we have is that for sufficiently large n, the ratio of successive terms is less than 1. Okay, so an plus 1 is smaller than an. Okay, so for large enough n, an is decreasing.
Mm-hmm.
Okay, so for large enough n, so the sequence might not be decreasing to start with, but eventually it must be decreasing. Eventually we must always have an plus 1 over an is strictly less than 1. Okay, so an plus 1 is less than an. Okay, so if the sequence is eventually decreasing, then the sequence is certainly bounded. Okay, so if an plus 1 is bounded, okay, we can just take the supremum of a whole sequence of ANs. Okay, so this is just some constant. Okay, so this is less than L plus epsilon to the n minus capital N minus 1 times some constant k. So what have we shown? Well, we've shown that eventually all of the terms in the series are less than something that's less than 1 to the power of n. Okay, this is just a constant which doesn't really matter. Okay. Okay, but the sequence x to the series n is into x to the n. Well, that series converges if x is less than 1. Okay, so by comparison, we've shown that an converges. So in fact, this isn't quite a normal proof. You know, normally we start by saying let epsilon greater than 0, and we want it to be an arbitrary epsilon. In fact, we don't even need an arbitrary epsilon here. We could have just taken epsilon equals to 1 minus L over 2, say. As long as L plus epsilon is less than 1, that's all we need. Because all we're trying to get is we're trying to get an upper bound on the terms of this series AN. Okay, so we're bounding by something less than 1 to some power. If you like. So I just rubbed something out there because this thing, the L plus epsilon to the power of minus n minus 1, we can just put that into the constant. You know, that's just another term in the constant. Okay, so then we're using the comparison test with this series and the series of the form x to the n. Does that make sense?
Mm-hmm. Okay.
Where did I lose you?
No, I'm just thinking of it again.
So okay, so to recap the whole proof, we know that this thing converges, this ratio converges. Okay, so let's just take epsilon equal to 1 minus L over 2. Okay, then L plus epsilon is equal to epsilon is equal to mass L plus 1 minus L over 2. So that's equal to L. So we've got L minus L over 2, and we've got a half. So we've got a half L. I'm being stupid. A half minus L over. That can't be right. I made a mistake. Basic algebra. I can't do basic algebra. Something it seems wrong. So we've got two.
No, that is okay. I
Right,
think half
okay.
here minus L, but maybe there's something wrong between your first and second line. Oh no. Okay, so you added L, right? Yeah, okay.
Okay, well, so let me just put some numbers in. So if L was 0.9, this would be 0.1 divided by 2, so 0.05. So we've got 0.9 plus 0. So this would be like 0.95. We can't possibly be right. Because that's something negative. What have I done wrong? Jonathan? So suppose we take epsilon is 1 minus L over 2. That's the difference between L is less than 1. There's a difference between 1 and L. Where am I being stupid? So L plus epsilon is that. So, you know, if L was 0.9, say, then epsilon would be 0.05, right?
Okay.
Yeah, does that make sense? So L plus epsilon should be 0.95.
So what's the problem?
Well, because this doesn't look right to me.
Why not?
Because if...
L's less than 1.
Yeah, okay. Yeah. Yeah.
Oh, hang on. L plus epsilon.
L plus epsilon.
So it's... Because 2 plus 1... It's 3 over 2. It's 3 over 2 minus L over 2.
So this is 2L plus 1 minus L over 2.
No, that's a 1. That's not an L. The term on the left hand. Oh, no, it is.
This is
Yeah,
an
it
L.
is, yeah.
So it's 3L. So it's half plus
I
L over
can't-
2. It's half plus.
Half plus L over 2 would make a lot more sense,
Yeah.
but what? But
Yeah.
that's what it
It's
ought
the
to
L's and
be.
the 1s are confusing.
1 plus L divided by 2. So what? How did you get that? Because that's plus minus. What? Am I being crazy?
Yeah, because it's 2L minus L is L over 2.
Yeah. Okay. God, I can't do algebra. it's come to that point. Okay, so what are we doing? We're recapping the proof. So we started by assuming this. Okay, so we have ratio of successive terms converging to some limit. Let's suppose that limit is less than 1. Let's take epsilon is this thing. Okay, so L plus epsilon is 1 plus L over 2, which is strictly less than 1. Okay, so by the definition of a limit, we know that some capital N, such that for all n bigger than capital N, an plus 1 over an minus L is less than our epsilon. Okay, so by the normal trick, an plus 1 over an is certainly less than L plus epsilon. Okay, but L plus epsilon is strictly less than 1, just showed. Okay, so for n bigger than n, an plus 1 is bigger than an. Okay.
It should be bigger or
Less than.
Yeah.
Yeah. You're paying attention. An plus 1 is less than an. So we're seeing this is decreasing. Okay, now let's have a look at what an is. And you could do the same thing on the lower bound, and you know, in fact this must be true for absolute values as well. This is really what we do. So what is the absolute value of an? Well, that's an times n over minus 1. These things cancel out, okay? So we can write an in this way, this kind of slightly strange way. So in total we have n minus capital N minus 1 terms that look like this, and then we have this final term. Okay, each of these terms is a ratio, okay, and the top and bottom are bigger than capital N. Okay, so we know that the top and bottom are all less than L plus epsilon. These ratios are all less than L plus epsilon. Okay. And then we just have the final term. The series must be bounded because it's eventually decreasing. It's something of a form L plus epsilon to the n times some constant. So it's less than something times L plus epsilon to the n times some constant. But this is less than 1. Okay, so what we've proven is that the absolute value of an is always less than some constant to the power of something less than 1. But we know that series of the form n is 1 to infinity, x to the power of n, they converge if x is less than 1. And that was one of the exercises which we didn't go through. I've been a bit lax with absolute values, but fill in the gaps. Okay, so that's for ratio test, which is a bit easy way of seeing for series convergence. So there are some nice examples to get some point to all of this. There's another one here which I won't go through the proof of, the nth root test. I don't remember ever using this one. The lim sub of the absolute value of an to the power of 1 over n. So an to the power of 1 over n. Not the limit for lim sub. Do you remember the definition of lim sub?
It's the maximum,
Not the maximum, the supremum. So if you define, so it's the limit as n, as like capital N goes to infinity, of the supremum of the set
which is the highest.
x n greater than capital N. Okay, so you start at some point capital N, and you look at the supremum of the series from then on. Okay, and then you take the limit of that, moving the point you start further and further into the future. And supremum, you wanted to say the maximum. So for a finite set, the supremum is the maximum. The supremum is the least upper bound. Okay, so if you have half, 3 over 3/4, 5/8, 15/16, etc., etc. Okay, this is a set. Well, the supremum of this is 1, but 1 isn't in the set. So 1 is the supremum, but not the maximum. That set doesn't have a maximum.
Okay.
And this test says that if this lim sub of an to the power of 1 over n tends to some limit L greater than 1, then it's going to diverge, otherwise it's going to converge. So those tests together are quite useful. So for example, do you recognise this? Can you see that very well? So sum n is 0 to infinity, x to the n over n factorial. Do you recognise that?
Sure, I've seen it in like financial theory or something. Class. Looking at it, I don't know, I can't remember, some CAP-M model or something.
Okay, it's possible. So, well, let's just look at the first few terms of that. So that's 1 plus, so do you know what this exclamation mark is? So that's for factorial. So n factorial is n times n minus 1 times n minus 2, all the way up to 1. Okay, so 1 factorial is equal to 1, 2 factorial is equal to 1 times 2, which is 2, 3 factorial is equal to 1, 2, 3, which is 6. Okay? So this sequence is 1 plus 0 factorial is 1 by kind of convention. So this is 1 plus x squared over 2 plus x cubed over 6, etc., etc. Still don't recognise that? No? So if you take...
So that's like, you would...
So this is the Taylor. So it looks like a Taylor series. That was where you were going with that. So the question is, what's it the Taylor series of? Do I know? I thought I did, but then I thought that's probably wrong. Just 1 second. Oh, yeah, I did know. I was trying to start with. So let's look at e to the x. Okay, so suppose f of x is equal to e to the x, then f dashed of x, the first derivative of f of x, is e to the x. Second derivative, yeah, okay, is also e to the x, etc., etc., etc. Yeah, and if you remember, so for any fn is the nth derivative, so the nth derivative of x is also e to the x. So if we take the Taylor series of e to the x around 0, okay, all of these things are e to the 0, which is 1. Okay, so all of these derivatives are equal to 1 at 0. And okay, we'll look at Taylor series shortly, but the definition of a Taylor series is that you take x to the n over n factorial times the nth derivative of x at that point. You're taking the derivative. Okay, so for e to the x, these things are all 1. So this series is converging to e to the x. And in fact, this is normally what people take as the definition of e to the x. Okay, so the question is, does e to the x exist? Well, we can show that it does by the ratio test. Okay, if we look at the ratio of successive terms, we have xn plus 1 over n plus 1 factorial. Get rid of so we have this divided by x to the n over n factorial. Okay, so this is one term divided by the other term. Well, this is, we have an n fact, okay, so let's write it as x to the n plus 1 times n factorial divided by x to the n times n plus 1 factorial. Okay, so x to the n plus 1 divided by x to the n is just x. Yeah. N factorial divided by n plus 1 factorial.
1 over n plus 1.
Yeah, exactly. Yep. So this is the absolute value of x over n plus 1. So for the ratio test, we need the ratio of successive terms to converge to some limit, and hopefully that limit is less than 1. Well, if x is less than 1, well, this, yeah, it doesn't matter. This is going to converge to 0 as n goes to infinity. Right, this is just, x is just some constant, so as n goes to infinity, this is going to 0. So we've proven that the ratio of successive terms goes to 0, therefore this series exists for any x. Okay. So we've defined the exponential function. One useful thing that you'll see a lot is, well, maybe a lot is an exaggeration, but people talk about absolute convergence of a series or conditional convergence. So a series converges absolutely if the sum of the absolute values of the elements is a convergent series. Okay, so it can be the case that n is not this series. It can be the case that this series converges, but this one doesn't. Okay, so in that case we say it's conditionally convergent. But these sequences which are absolutely convergent, where both things converge, they're a lot better behaved. They're well-behaved sequences in some sense. And if a sequence converges absolutely, then it certainly converges in levels without the absolute sign. And this is just because of the comparison test. Right, the comparison test said that if absolute value of an is less or equal to bn, and bn converges, then we're okay. So if we just take bn equal to the absolute value of an, then this says that the absolute value of an is less or equal to absolute value of an, which is certainly true. Okay, so any absolutely convergent series also converges by the comparison test. So for an example, yeah, so sum n is 1 to infinity minus 1 to the n plus 1 divided by n, that converges. Okay, so we showed that before, I think. Yeah, here. Okay, so 1 minus a half plus a third. But we know that the series 1 over n, we know that series doesn't converge. Okay. But remember, that was like kind of log of the upper bound, which is going to infinity. So not all series are absolutely convergent. And if a series is absolutely convergent, then you can reorder the terms in the series without making any difference to the answer. Yeah, so here's what can go wrong if you start reordering terms with non-absolutely convergent series. So naught is naught plus naught plus naught plus naught. Well, naught is just equal to 1 minus 1, so let's write it like that. So we have 1 minus 1 plus 1 minus 1. Well, now let's do what I did before. Let's bracket as 1 plus minus 1 plus 1 plus minus 1 plus 1. Okay, so we have 1 plus naught, 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 which is equal to 1, clearly. So we have naught is equal to 1. So if you start messing around with series, you can get crazy things. So the point at which you did something you shouldn't have done is kind of, I guess, from there to there is not a valid step. Well, yeah, I suppose the problem is here, when you write down this series, this is a series that converges. Okay, so this doesn't actually mean anything. This dot 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 doesn't mean anything. But if a series is absolutely convergent, then you can rearrange the elements without doing any damage. These are exercises. Okay, shall we take a break? What time is it? When are we supposed to finish? We're supposed to finish at... Oh yeah, okay, it's a good time to take a break. Okay, good. Should we carry on?
Mm-hmm.
Okay, so I think that's all we have to say about sequences and series. So now, rather than talking about limits of sequences, we're going to move on to talking about limits of functions, and we're going to get on to continuity as well, hopefully. So very briefly, what is a function? I think you know this. So, you know, a function is a mapping from some set A to a set B. Okay, we normally write f maps A to B. Okay, means f is a function mapping from A to B. We call A the domain of the function, B the range of the function. People write f of A for the image of the function. So f of A is the set f of x such that x is in A. Okay, so this is the set of all points that A takes. Yeah, so that's the image. The image is not necessarily the same as the range, but it's always a subset of the range. No, I've got it so. You'll be the whole. Look all these things. Just a sec, let me just put it on my side. It's just terminology. I forget the terminology sometimes. So, sorry. So this thing, f of A, is the range. B people call the codomain, I think. Okay, so but f of A is just some subset of B. Okay, it won't necessarily be the whole set. So we can skip all these examples. We know what functions are. You know what a polynomial is. Okay, it's powers x squared times some coefficient. A rational function is a ratio of two polynomials. Yeah, you can take linear. You can combine functions in various ways. So it's useful to work with to be able to define operations on functions. Okay, so in my macro course later on, you'll work with spaces of functions. So the function fg is a function defined by f of g of x is f of x times g of x. Okay, so we can multiply functions directly. Okay, or we can add functions together. So this is just notation, really. We call a function injective. Okay, injective, or just 1, 1. So you can call it either injective or you call it 1, 1. If for all B1, no, for all A1, A2 in A, okay, if f of A1 equals f of A2, then A1 equals A2. Okay, so a function is injective if whenever this is true, then that is true. Okay, so what's this saying? It's injective if whenever two values of a function map to the same point, then they must have been the same point to start with. Okay, so this is saying, it's another way of saying that the function never takes the same value twice. That's another way you could say it, I suppose. Okay, so
I don't understand why that's true. They might have.
Well, it's not true in general. This is
Oh.
So this is the definition of being injective or 1-1.
Oh, sorry, I missed that.
Okay.
Important bit of.
Okay, so this is a property that we might like a function to have. Okay, so if you think of y is x, there's y is x squared. Okay, is this injective?
No.
No. Okay, because suppose we take this point, and this point. Well, f of this point is equal to f of that point, but that point doesn't equal that point.
Is that the same as being monotonic?
No, monotonic. Well, yeah. So monotonic is always increasing or decreasing. Any strictly monotonic function is 1-1. Yeah. Any strictly monotonic function is injective. But this is defined on sets A and B where we don't necessarily have an order. Okay, there might not be an order on A and B. Okay, so you can't talk about being monotonic in that case. So this is what people talk about normally. So this is one useful property of a function. Another is being onto. So we say f maps A to B is onto if f of A is equal to B. Okay, so it's the image of A is just the whole set. Okay, so so you can write that another way as for all B in B, there exists some A in A such that f of A is equal to B. Okay, so for any point in the codomain, there's some point in the domain such that f maps that point to that. Okay, so again, y is x. If we think about f mapping from R to R, defined by f of x equals x squared, is that onto? No, because it never takes negative values.
So
onto means this. That f of A is equal to B, or equivalently, that for any set in B, we can find an A such that f of A is B. So if we think of f as mapping from the real numbers to the real numbers defined by f of x as x squared, then this never takes negative values.
Yeah.
So for any negative value, say -1, we can't find an x such that f of something is equal to -1. Okay, so this isn't onto. But if we took from the reals to the positive reals, then kind of with that redefinition of the function, then it's onto. So being onto is kind of a property of the definition. And if a function is both injective and onto, so or 1-1 and onto, we call it bijective, or a bijection. Okay, these are just terminology. So any bijection has an inverse. So if a function is 1-1 and onto, then well, because it's onto, we know that so here's f maps A to B. We want to prove that if f is bijective, then f has an inverse. What does it mean for f to have an inverse? It means we can write down a function f inverse mapping from B to A. Okay, which is such that f of f inverse of x is equal to x. Well, because it's onto, we know that for any point in B, there's at least one point that maps to that point. Okay, and because it's injective, we know that there's precisely one. Okay, so onto means there's at least one point that maps to any point in B. 1-1 means that there's at most one point that maps to any point in B. Okay, so if there's at least one and at most 1, but there must be exactly 1. So these two things together mean for every point in B, there's a unique point in A such that f of A is equal to B. Okay, so we define the inverse to be that unique point. What else is to say? We say a function is bounded if its image is bounded. Okay, so f is bounded if this set f of A is bounded. And then we can look at the supremum of this set. Okay, so this is the supremum of the image of the function f on A. So it may or may not be the case for this. So this is, we can write this as the supremum of the set f of A in A. Okay. If this set has a maximum, that means, so in the case this set has a maximum, it means for some A star, such that f of A star is greater than f of A for greater equal to f of A for all A in A. If it has a maximum, but it might not have a maximum. Okay, so this supremum could be something different. For example, well, if we think about if you want, okay, so f maps positive reals to reals given by f of x is log of x. Okay, then, well, that doesn't even have a supremum. I was trying to think of an example which has a supremum but not a maximum. Well, you can kind of do a slightly cheating example. So suppose we take f from the open interval 0, 1 to R. Okay, defined by f of x equals x. We're kind of cheated by taking an open interval, but this is fine. Well, what's the supremum? So the supremum of f of the open interval 0, 1 is clearly equal to 1, but there's no point at which. Okay. So it's a bit of a cheating example. Let's carry on. Okay, so a limit of a function. Do I like the way this textbook does it? Not really. Well, we'll do it this way. Okay, so the way this textbook introduces limits is it first introduces left-hand limits, then it introduces right-hand limits, and then a limit is something that's both a left-hand limit and a right-hand limit. So a limit from the left is, you're kind of following the graph of the function, and you're getting closer and closer in from one side. Okay. And what do we write? You can see it there. So we write that f of x tends to L as x tends to b minus. Okay, so the minus sign on the end means we're converging from the left. Like minus is, if you think of a real line, minus is on the left-hand side. Or you write that lim x tends to b minus f of x is equal to L. And what does this mean? Well, it means that for all epsilon greater than 0, there exists some delta greater than 0, such that for all x in the interval b minus delta comma b. So this is the open interval. F absolute value of f of x minus L is less than epsilon. Okay, so note that we don't include the endpoint. So it doesn't have to be the case that f of b minus L is less than epsilon. Okay, so the function might do something very strange at the actual point of a limit. So for example, if you think of a function, how can I do this? So this function is called the step function. F of x equals 0 if x is less than 0, or 1 if x is greater or equal to 1. Greater or equal to 0. Well, what's lim? So f of 0 is equal to 1. Okay, but lim x tend to 0 minus f of x is equal to 0. Okay, because as x tends to 0 from the left hand side, we're always at 0. Okay, so we don't include the endpoint there. So really, this is very similar to the definition of a limit of a sequence, whereas before we had there exists a capital N such that for sufficiently for n bigger than capital N, we were close to the point. Now we're saying there exists a delta such that if you're in a close enough region around the point, then fx minus L is less than epsilon. Okay, so if we're thinking, here's our function maybe, okay, and we want the limit at, I don't know, this point. What are we saying? Well, we're saying give me an epsilon bigger than 0. So if you give me an epsilon, so I'm saying this is the limit. So here's L, here's L minus epsilon, here's L plus epsilon. Okay. So you're giving me a limit, and I'm saying, well, I can find a delta such that if we're close, such that if we're in this interval from what's this? This is b, so this is b minus delta up to delta, then the point is within the limit. Okay, it's not a very good diagram. Can you? Yeah, you see it. Okay. So as we get sufficiently close to this point b, f of x becomes sufficiently close to the limit. Okay, so this is a left-hand limit. You can also define a right-hand limit. Okay, for a right-hand limit, we replace b minuses with b pluses, and this becomes x in b plus delta. Okay. And then a limit, so we say that f of x tends to, that's an L, put it on that, L, as x tends to b, without a plus or a minus, if it's both a left-hand limit and a right-hand limit. And this is equivalent to saying that for all x in b minus delta, b plus delta. Okay. So you can write this as for all x are such that x minus b is less than delta. So this is the definition of the limit. And really, the properties of limits of functions are very similar to the properties of limits of sequences. So we can combine them in the same way. so this book goes on to define continuity in terms of limits. So they say that a function is continuous at a point if and only if the so they say so we've got this function f from a to b. They say f is continuous, normally abbreviated CTS, at x star if and only if the limit as x tends to x star of f of x is equal to I don't like the way they do it. So, well, this thing has to be. We're lots of slightly different definitions of these concepts. So I'll do it roughly the same way as them, but not exactly the same. Okay. So this is a clearer definition. If lim x tends to x star minus f of x is equal to lim x tends to x star plus f of x, which is equal to f of x star. Okay, so you're continuous at a point if the left-hand limit is equal to the right-hand limit, which is also equal to the value of the function. Okay, so writing it like this makes it clearer the different ways that you can fail to be continuous. So if we think of a function, so think about being continuous at this point here. So we can have a function that was carried on like this, and up to that point it was like that, but then at that point it jumped up to here. Okay, so this is the way we normally draw jumps in a graph. We have a circle for this point is not included, a coloured in circle for this point is included. Okay, so here the left-hand limit is here, the right-hand limit is there, the value is there. So this isn't continuous at that point, because so these two things are the same, but this isn't the same as those two things. We could also have a case where the function was going along happily. The left-hand limit is equal to the right-hand limit, okay, but the value of that point is something crazy. Okay, so you can have maybe x is, I don't know, x if x is not equal to 0, or 1 if x equals 0. Yeah, that's a perfectly well-defined function. It's a crazy function, but the left-hand limit of this at 0 is 0, the right-hand limit of this at 0 is 0, but the value of the function at that point is 1. Okay, so that's not continuous either. But so this is one way we can define continuity. Normally, people prove this as a consequence of a different definition of continuity. So what people normally take as the definition of continuity is this: f is continuous at x star if and only if for all epsilon greater than 0 there exists delta. It's just the same. No, it's just the same thing, I suppose. For all x in R, it's just the same thing, isn't it? X minus x star plus delta, f of x minus f of x star is less than epsilon. It's a long line. Okay, so this is it's just what I defined as the limit of the function. Let me just check that I haven't made a mistake. Okay, so this is what's normally taken as the definition of continuity. This is the same as I defined. Yeah, so but I made a mistake previously. So before I defined, let me just go back slightly. So I said lim x tends to be f of x equals L if for all epsilon greater than naught there exists delta greater than naught such that for all x in x minus delta x plus delta f of x minus L is less than epsilon. And this isn't quite right actually what I told you a second ago. So really what we want is this interval from x minus delta up to x plus delta, but not including x. Okay, for a limit we don't care what the value of the point is at that point. So in this example I showed you before, where we had a funny function that was kind of then jumping up here, the limit of the function at that point is here. Okay, so it's perfectly well defined, the limit at that point. So what I should have said is x minus delta comma naught union naught comma x minus delta comma x comma x plus delta. Okay, so the limit of a function is equal to L just if the left hand limit and the right hand limit are equal to L. It really is just the combination of the left hand limit and right hand limit definitions. Sorry, I went a bit too far. Okay, so f is continuous if the limit is equal to the function value. Or equivalently if this is true. So so how does this differ to that definition of a limit that we had? So the definition of a limit would have had would not have included the point x equal to x star. Okay, but for it to be continuous, it has to be tending to that point anyway, so it doesn't actually matter that we include the point x as x star. So this is normally the definition people take as the definition of continuity. Okay, so to draw it in a picture, let's just use this one again. So if we take a point x star, is the function continuous at that point? Well, let me draw a more interesting function. Okay, so here's a function that certainly looks continuous, it's nice and smooth. So the definition says you give me an epsilon. Okay, so maybe this little distance here is epsilon. So you give me a range, if you like, then I can find a delta such that if x is in a range around that delta, a range around x star of width delta, then f of x is going to be within this range that you gave me to start with. Okay. So, locally the function is smooth. It's locally it's all close together, if you like. So that's the definition of continuity that people normally use. Sorry for slight mistake. Get back. Yeah. So do we prove properties of limits? Doesn't seem to have done. Okay, so we can prove some There's properties of limits. So we'll talk more about continuity in the next chapter, I think. So for now we just have the definition. Okay, so before we were looking at convergent sequences, and now we've got, so we had limits of sequences, now we have limits of functions. You'd hope there'd be a relationship between the two. What this theorem says is that f of x tends to L as x tends to something z, if and only if for every sequence of points tending to z, f of xn of that sequence tends to n. I'll just write it again. Okay, so the claim is that f of x tends to L as x tends to x star, if and only if. So people normally write IFF for if and only if. For all sequences xn with xn not equal to x star for all n, f of xn tends to L as xn tends as n tends to infinity. Okay, so on the right hand side we have convergence of functions. So f of x tends to L as x tends to this point x star. On the right hand side we have convergence of sequence. Excuse me. So we say for any possible sequence xn where the elements are never exactly equal to x star, f of the elements of that sequence converges to L as n goes to infinity. Okay, so we're going to be two steps to the proof. First we have to prove this implies that, then we have to prove that implies that. Okay, so let's do this direction first, going that way. Okay, so suppose f of x tends to L as x tends to x star. Move. Okay, then, so we're assuming this, and we want to prove this thing. Okay, so we want to prove something with starting with a for all. So whenever we want to prove something starting with a for all, we always write let xn be a. We always start with a let. Okay, we take a particular case and prove that it holds for that particular case. Let xn be a sequence with xn not equal to x star for n. Okay, so what we want to prove then is that f of xn tends to L as n goes to infinity. Okay, so again, the definition of this starts with a for all, so we're going to have a let epsilon greater than 0. Okay, then, because we know f of x tends to L as x tends to infinity, we know there exists delta greater than 0 such that for all x in x minus delta x star union x star x plus delta f of x n minus L is less than epsilon. Okay, so what we have here is that what we have here is that for all x sufficiently close to our limit, f is, so all x sufficiently close to x star, f of x is sufficiently close to L. Do we need that to be convergent? Do we assume that? Sorry, what's the claim? 3? Yeah. So we all sequence x and we miss something. Xn has to converge to x star. Xn tends to x star as n goes to infinity. So we've got, is that clear? So given a sequence xn which is converging to x star, the claim is that f of that sequence will converge to L. Okay. So here we're trying to prove that this thing implies this thing. So we know that this is true. We also know that this is true. Okay, so we also know that there exists n in n such that for all n bigger than n, absolute value of xn minus x star is less than delta. Okay, so this is because f of x tends to L as f of x tends to L as x goes to x star. This is because xn tends to x star as n goes to infinity. So we can combine these two things, right? This is saying for sufficiently large n, I've got it. I've been too smart. So remember the definition of convergence of a limit we normally say is less than epsilon. Okay, but epsilon is arbitrary. In particular, we can take epsilon as equal to delta, which is what I've done here, kind of without thinking. Okay, so we know because xn tends to x star that given this delta, so we've already found the delta from the definition of continuity. Given that delta, we can then find a capital N such that xn minus x star is less than delta. Okay, so if you kind of follow back, n will be a function of delta. Delta is itself a function of epsilon. Okay, but that doesn't matter. So we know that for n bigger than n, xn minus x star is less than delta. So this is certainly true. Okay, it's certainly the case that. So this implies that xn is in x star minus delta, x star union x star plus delta, because we assumed that xn was never exactly equal to x star. Okay, therefore, from this continuity statement, we know that f of xn minus L is less than epsilon. Okay, so we've proven that way. Does that make sense? Okay, so we're proving that f of x tends to L as x goes to x star implies this. Okay, so we're assuming that we take xn to be an arbitrary sequence, we take epsilon to be an arbitrary constant, then by the definition of convergence and limits of f, there is some delta such that for x sufficiently close to x star, f of x minus L is less than epsilon. But then let's take this delta and plug it into the definition of convergence of this sequence xn as n goes to infinity. So there must be a capital N such that for little n bigger than capital N, xn minus x star is less than delta. So then xn must be xn must be between x star minus delta and x star plus delta, but we assumed that xn is never equal to x star. That was part of the theorem, so it's in the union of these two intervals. Okay, therefore this thing applies to it, applies to x, and it applies to xn. Therefore, f of xn minus L is less than epsilon. Okay. Is that clear? Okay, so we've proven that this thing implies that thing. Now we just have to do the opposite direction. So that direction. So we're going to suppose that this is true. Okay, so suppose for all sequences, I can't bother to write it again, but it's just that thing. And we want to prove that f of x tends to L as x tends to x star. Okay, so let's have epsilon greater than 0 again. It's probably easiest to do it by contradiction. Okay, so we want to prove that this thing implies that. So, so we're assuming that this is true. Let's suppose that this isn't true. Okay, and if that generates a contradiction, then we're done. Okay, so let's suppose that it's the case that f of x does not converge, does not tend to L as x tends to x star. Okay, so it's not the case that. Okay, so remember, so this symbol means not. Okay, funny thing. So it's not the case that for all epsilon greater than 0, there exists delta greater than 0 such that for all x in x star minus delta x star plus x star union x star. Okay, so this is what flies out of a not sign is just our definition of the limit. Okay, for all epsilon greater than 0 exists delta such that for all x in these regions, fx minus L is less than epsilon. So this is not true. Well, that means, remember what I said earlier, that when the not of a for all is of there exists, if you want to disprove that something is always true, you just have to find a single counterexample. So this means that there exists epsilon greater than 0 such that for all delta greater than 0, there exists x in x star minus delta x star union such that this thing isn't true. Okay, so all you do to negate one of these expressions with for alls and exists is you just swap all of the for alls into exists and vice versa. Okay, so we know there exists an epsilon greater than 0 such that for all delta there exists some x such that fx minus L is at least that distance away. Okay. And we want to get a contradiction from the claim about sequences. So what we want to do is we want to use this to construct a sequence that doesn't converge. Okay, so this says there exists some epsilon for which that's true. So let's just take that particular value of epsilon, and let's define delta n equals 1 over n. Okay, so that's a sequence of progressively smaller deltas. Okay, so then this. Okay, so this is defined. People often write, mathematicians often write delta colon equals for defining something. So colon then an equal sign means define this thing to be that thing. So define delta n is 1 over n. Then from this statement, okay, we know there must exist an xn in x star minus delta n, x star union x star plus delta n, such that absolute value of f x n minus L is greater or equal to
On that last one, if you're saying that not for all epsilon blah blah blah, and you're changing that just to be there exists, shouldn't the last expression be the same?
So, well, let me give an example. So, suppose you have the claim, it's not the case that for all x in R, x is greater than 0. Okay? Which is certainly true, right? It's not the case that for all x in R, x is positive. Well, let's do it this way. This means there exists x in R such that x is less or equal to 0. You know, to get a counterexample, how do you find a counterexample to this claim that for all x in R, x is positive? Well, you just have to find a single negative. Okay. So not that, it means that.
Okay.
So what have we done? We defined delta n as 1 over n. Okay, then this is true for all delta. So we know we can find some xn in this set such that absolute value of f of xn minus L is bigger than epsilon. Okay, so we've got a sequence here, xn. Well, what do we know about this sequence? This sequence, element xn is always within distance 1 over n of x star. Okay, so yeah, so certainly the case for xn minus x star is less than 1 over n. That's what we have. So xn tends to x star as n goes to infinity. So we have here a sequence which is tending to x star, but f of xn minus L is always greater or equal to this constant epsilon. Okay, so there's some lower bound on the difference between f of xn minus L. Okay, so in particular this means that f of xn does not tend to L as n tends to infinity. Okay, which is the required contradiction. Okay, because we were proving that this thing implied that thing. Okay, so we're assuming that for all sequences xn with xn tending to x star, f of xn tends to L. Well, here we've constructed a sequence of xn tending to x star, but f of xn minus L was always bigger than something, so there's no way that f of xn could be converging to L.
Mm-hmm.
You done?
Yeah. Mm-hmm.
Okay. Is that clear?
Yeah.
So what did we prove? We've proven that so there's a nice relationship between convergence of sequences and convergence of functions. So this also gives another definition of continuity, right? Because something was continuous if the limit was equal to the value of the point, so we can also say that something is continuous if all possible sequences converge to that point. So there are lots of definitions of continuities. Did they prove it the same way? Yeah, they did exactly the same. Okay. The exercises. It's difficult. Okay, so remember that we proved for sequences that linear combinations of sequences converge to linear combinations of limits, products of sequences converge to products of limits, ratios of sequences converge to ratios of limits. Because of what we just proved, okay, that there's this relationship between convergence of sequences and convergence of functions, we can derive from our old results the same things hold for limits of functions, okay? So, again, linear combinations of limits of functions converge to linear combinations of their limits, etc., etc. So, yeah, okay, so this implies that a polynomial is continuous at every point. Well, because x to the n is x times x times x. Okay, so well, we haven't proven that f of x equals x is continuous, have we? So why is that continuous? Well, okay, so let's prove it. Let epsilon greater than 0. Okay, then if x minus x star is less than epsilon, then f of x minus f of x star is less than epsilon, because f of x is just equal to f of x star. So we can just take, so that implies that, take delta equals epsilon in the definition of continuity, and we're done. Okay, remember, for the definition of continuity said that for any epsilon, there was some delta such that if x minus x star was less than delta, then f of x minus f of x star would be less than epsilon. Okay, so here's some delta equal to epsilon. So f of x equals x is continuous. Because products of limits converge to limits of products, we know that if f of x is continuous at some point, then f of x equals x. So if x is continuous at some point, then x squared must be continuous at some point as well. Okay, because x squared is continuous at A, and x, so let me write it down. X squared is CTS at x star, if and only if, let's do it in terms of limits, lim x tends to x star, f of x equals f of x star. Okay, that's just a definition of continuity. But limits of products are products of limits. Okay, so the limit as x goes to x star of f of x is limit x goes to x star x times limit x goes to x star x. Okay, which is x star times x star. Okay, which is f of x star. Okay, it's kind of obvious, right? So, and you can do that for higher powers, obviously. You can do that for linear combinations. So basically, all of the properties we found for limits are also true for continuity. That's what it gives you. So polynomials are continuous. Rational functions are continuous at every point where the denominator isn't 0. Okay. And there's an analogue to the, remember for limits of sequences we had the sandwich theorem, okay, where if you had one sequence, so we had xn less or equal to yn less or equal to zn, xn was converging to L, zn was converging to L, then the sandwich theorem said that yn must converge to L as well. Well, we have the analogue here. If we have g of x is less or equal to f of x is less or equal to h of x, okay, then if g of x is converging to some point as x goes to x star, then h of x must also be, and h of x is converging to the same point, okay, then f of x must be converging to the same point. So limits of sequences really act just like limits of functions. What's that? I can't read that. What's new with functions is that we can also take compositions of functions. Okay, so we can take the function h of x is equal to f of g of x. Which is sometimes written f circle g. So this circle operator is composition. So we'd like to know how the limit of h of x acts as a function of the limits of f of x and g of x, because that will enable us to increase the range of limits we can work out. F is continued. Okay, so the theorem says, suppose either of the following somewhere due to g of x. Okay, we're gonna, so it gives two different conditions to ensure that f of g of x tends to, for limit as x tends to something. We're going to ignore the second condition because it's not very useful, but let's talk about this first condition, which is the important one. Okay, so what do we need? F is continuous. Okay. Yeah. Okay, so suppose we have that as g as x tends to x star, g of x tends to y star, and suppose that as y tends to y star, f of y tends to f of y star. Okay, so is that all we need? What do they have? They just take some two points. And F L is F. That's it. Okay. And we define H like this. So our claim is that that's an arrow, sorry. That H of x tends to f of y star as x tends to x star. Okay, so it's kind of intuitive. So how are we going to do it? Well, so this is saying that f is continuous at y.
That can be an or rather than and. It's one or the other. It says is sufficient to.
No, we're ignoring the second condition. This is the statement of the theorem and the first condition combined into one. The second condition isn't very interesting, I think.
Okay.
Maybe it's useful for something, but this is the most important. You see why? So the theorem said, suppose that the two things were converging. Okay, so the theorem said this tends to L, and then the first condition was L equals f of y star.
Okay.
Yeah. Okay, so here's our claim. So, as ever, we want to start with let epsilon greater than 0. Okay, so from this statement, okay, we know there exists delta greater than 0 such that for all x in for y in y star minus delta y star union y star plus delta f absolute value of f of y minus f of y star is less than epsilon. We doing this in the right order? Okay, so we've got a delta now. So let's, in the definition of this limit, let's take the epsilon in the definition of this limit to be this delta. Okay, so then plugging that delta in, we know that, so let's call this delta 1 actually. Delta 1. Okay, so we know then that there exists delta 2 greater than 0, such that for all x in x star minus delta 2, x star union x star plus delta, g of x minus y star is less than delta. It's less than delta 1. Okay, so normally we'd have, normally this would be a less than epsilon, but it's true for all epsilon. In particular, it's true for epsilon equals delta 1. Okay, so we have that g of x minus y star is less than delta 1. So for x sufficiently close to x star, g of x minus y star is close to delta 1. How close is it? Well, it's sufficiently close, right? It's in this set, or possibly it's equal. Possibly it's equal, but we know. Okay, so if you like, for two cases, if it's equal, then we know that f of y minus f of y star is equal to 0, so it's certainly less than epsilon. Okay, so otherwise it's in this set. Okay, so because g of x is in this set, again, let me just write it this way. So it implies g of x is in the set y star minus delta 1 y star union y star plus delta 1. It implies either this is true, or g of x is exactly equal to y star. Okay. So in the first case implies that f of g of x minus f of y star is less than epsilon. Okay, the second case implies that f of g of x minus f of y star is equal to 0, which is certainly less than epsilon. You happy with that?
With the last line.
So from here
Yeah.
to we've got two cases. So we know that g of x minus y star is less than delta 1. So g of x is certainly in the interval from y star minus delta to y star plus delta. Okay, this is just the same as saying that y star minus delta is less than g of x. X is less than y star plus delta. Okay, so we distinguish two cases. One of them is that g of x is exactly equal to y star. The other one is that it's in that interval but not equal to y star. Okay, if it's in that interval but not equal to y star, then it's in this. Yeah.
Okay.
Yeah. So then, because it's in that, we know that f of our y, which here was g of x minus f of y star, is less than epsilon. Okay. In the other case, g of x is exactly equal to y star. So f of g of x minus f of y star, well, so g of x is equal to y star, so f of g of x is f of y star. So this is f of y star minus f of y star, which is just equal to 0. And 0 is certainly less than epsilon. So in the first case...
Yeah, I understood that, but the second one?
So the second case was g of x was equal to y star. Okay, so in that case, f of g of x is f of y star, because g of x is y star.
Okay.
Yeah, so we have f of y star minus f of y star, which is just 0.
Okay.
Okay, and 0 is 0, it's only less than epsilon. Okay, so a corollary of this theorem is that if we took y star if we took y star equal to f of g of x star, so if it's held with y star equal to g of x star, so that's saying that g is continuous at this point x star, then what we would have proved is that h was continuous at that point. Okay, so this is proving that compositions of continuous functions are continuous. That's effectively what we're proving. Where are you up to?
Yeah, yeah. Mm-hmm.
I think we've actually done some bits from the next chapter. Where's my clicker? So we've done that. Yeah, so just as before, rather than having convergence, sometimes things go to infinity. So we have divergence, so we write that f of x goes to infinity as x goes to some point if through any h, any constant, we can find a delta such that if x is in that region, then the function is bigger than h. So it's just like as we did for limits. Okay, so I should we do this very quickly. There's hardly anything here. So what do they say? So in this continuity chapter, okay, so far we've defined continuity at a point. Okay, we said a function was continuous at a point if the limit of that point was equal to the value of the function. We might want to define continuity over a region. Okay, so if for some open interval, we say f is continuous on the open interval if it's continuous at each point of the interval. Did we define continuous on the right? Yeah, so on an interval including its endpoint, so a compact interval, we say that the function is continuous on that interval if it's continuous on every point on the inside of the interval, so the open interval from a to b, and it's continuous on the right at a and continuous on the left at b. And I don't think I ever defined this, but continuous on the right means the right-hand limit of the function is equal to the value of the function. Right-hand limit of the function at a is equal to the value of the function at a. Continuous on the left at b means the left-hand limit of the function at b is equal to the value of the function at b. So here's a funny-looking function. It jumps at a and at b. Excuse me. But it's on the interval from inside from a to b. It's continuous. And for something to be continuous on a compact interval, it just means that the endpoints have to be included. Okay, so that's a coloured in dot. That's a coloured in dot. So polynomials are continuous on all intervals. 1 over x is continuous apart from at 0. Okay, so this is the definition, a kind of a restatement of the definition we had. So that encompasses everything. Okay, so suppose you have some set S, or some they call it. Suppose you have an interval I, then f is CTS continuous on I, if and only if, for all x in I, for all epsilon greater than 0, there exists delta greater than 0 such that for all x in R with x minus okay, let's call that still. Sorry, okay, so you don't have to worry about continuity on the left and continuity on the right if you just use this. Oh, sorry, for all x in I. Okay, all we have to do is restrict ourselves to points within the interval, and then we're okay. That's all it's saying. Can I rub this out? Yeah. Can't be much of this chapter. Oh, okay, yeah. Well, let's just, can we just take a 2-minute break, because we do have to do that. Can't concentrate. Sorry. It's funny this. So this is an important important result. They're saying that the continuous image of a compact interval is itself a compact interval. So this kind of, in fact, you can kind of generalize a lot of what we're doing. So rather than working with real numbers, you can work with general spaces. And in the general space, it's incredibly easy to prove this result. But it looks like it's going to be a little bit difficult in this case. Okay, so the claim is, you can see in this picture, that if this is continuous, then this is a compact interval. Okay, so it's maybe surprising that this is an interval, I guess. So, for example, we can't have a case, if you think about a discontinuous function, here's a discontinuous function. So here's a compact interval, but then the image of that looks like that, okay, it's no longer an interval.
Mm-hmm.
Okay, so so we're going to prove it in several parts by the look of it. Image of I under F is also an interval. Okay, so the first claim. Okay, so F is going to map from I to R, where I is a compact interval. Well, let's say A. Sorry. So F maps from AB to R is continuous. Okay, and the claim is that F of AB, okay, so the image is an interval. Okay, so for something to be an interval, it means there can't be any holes in it. Okay, so presume we're going to prove by contradiction. Easy to prove by contradiction. Can I do it my way? It's fine, let's just follow the proof from the book. It's less easy than I thought it was. Okay, so what does the book say? So to show that it's an interval, if we have two elements of so they're calling I equals AB. Okay, so if we have two elements y1 and y2 of f of I, then we want to show that for all lambda in f of in the interval from y1 to y2, f of lambda is in f of I. Okay, so we want to show that f of I is an interval, so all we have to do is if you pick 2 points, it should be the case for all points in between them are also in the interval. So they define these sets, so they define S equals X such that f of X is less or equal to lambda and T equals X such that f of X is greater or equal to lambda. Well, certainly it's the case that so y1 is less or equal to lambda, right? By construction. Okay, because lambda is between y1 and y2. So y1 is less or equal to lambda. And y1 and y2 are in the image of f, so there must be some x1 such that f of x1 equals y1 and f of x2 equals y2. Just by the definition of being in the image, right? So there must be some x1 such that f of x1 is equal to y1. So then x1 must be in S and x2 must be in T. Okay, so x1 is in S, x2 is in T. So these two sets aren't empty. Follows with a point of Also, every point of the interval I belongs to one or other of these sets. Yeah, so at any point, f of x is either less or equal to lambda, or it's bigger than lambda. Okay, so for any x, it must be in one of s or t. Okay, so that's clear, isn't it? Follows that a point of one of the sets is at zero distance from the other. So why is this? So by saying, so what they're saying, the claim is that there exists some s in s and t in t such that distance s minus t equals 0. Point of one of the sets is at zero distance from the other. So this is from an old exercise, but we can probably show that. I think this is probably not the claim. So the claim is that for all epsilon greater than 0, there exists s in s, t in t, such that s minus t is less than epsilon. Okay, so let's try and prove that claim. I think that's probably what they mean. And we're supposed to be able to prove this from the fact that every x must be in one of s or t. Well, it makes sense. So suppose it wasn't the case, let's prove by contradiction. Okay, so if it's not the case, then it must be that there exists epsilon greater than 0, such that for all s in s, t in t, absolute value of s minus t is greater or equal to epsilon. But then this is a, remember, so we have the S union T equals AB. Okay, because every point is in one or the other. So what this is saying is that there are some points in AB such that this is true. We can rewrite this as exists epsilon greater than 0. You know, this is true for all s in s and t in t. So okay, now so it's for one about so we've got 1 point. We've got the x1 is in S. Okay, so in particular, it's the case that for all sorry, just 1 second. I'm being stupid, aren't I? So this is by see exercise 213.6. Let's just remind ourselves of what that was. Because we didn't do it. 213.6. Hint. Suppose that s is less than t, where s in s and t in t. Let t naught. Okay. That's not easy. Okay. Let T naught equals x such for x in T and x is greater than s. Okay, so s less than T. Show that T naught is not empty and is bounded below. Is that right? B is in. So let's see if we can do it with a hint. So we've got so we're proving by contradiction. So for some epsilon greater than 0, such that for all s and t, this is true. Okay, so let's take s less than t, and we'll do what it says and define t naught as this set. So what is this? This is the set of all x in t where x is bigger than s. Okay, so isn't t in t naught? Why wouldn't that be true? T is in T. Yeah, T is in T. T is bigger than S by assumption. Okay, so we just chosen any S and T with S less than T. So this thing isn't empty, so that was easy. What's the infimum of this set T naught? Well, B. Okay, so let's call the infimum of the set T naught B. You know, the set is non-empty, so it has an infimum, and we're following its idea. So if it was the case for, so this is the first case, case 1, B in T naught. If this was the case, then it means for some B in T naught, well, for some B in T with B greater than S, such that it's the infimum, so it's a lower bound, such that for all T in for all x in T naught, B is a lower bound, it's an infimum, so B is less or equal to x. Okay, but this means for all x in T naught means for all x in T with x greater than S, B is less or equal to x. Okay, this is just a statement that B is the lower bound. So there's some, not very easy this, is it? So we've got the two sets, S and T. There's some B in T with B bigger than S. Okay, well T was bigger than S, such that all x in T with x bigger than S, B is less or equal to x. Okay, so B is less or equal to this is S less than x. Yeah. Let's just write this way around so I'm not confused. So B is bigger than S, so we have S is less than B is less or equal to x. B and T. Right, so So for any okay, so if B is in T naught, okay, then certainly B is bigger than S. Okay, so let X be in T, okay, then it's the case that sorry, I thought I had it for a second. Do shout out and help me at any point. Okay. Okay, so for any x in T, there are two possibilities, right? Either x is bigger than S, or x oh, we didn't show that it's bounded below, did we? Is T naught bounded below? Well, it is because yeah, T naught is certainly bounded below by A because it's a subset of our initial interval. So we didn't do that. It's a bit confusing using B, isn't it? Because I'd already. Pretty confusing. Just going to call that C so that we don't get confused down the line. Isn't the problem, but isn't that? Show me the two, zero distance from the other. Okay, so I kind of lost the intuition, which is why I'm struggling. So what is this set? Let's try and understand what this set is. We've got these 2 points S and T, one from one set, one from the other, and this is all points from T which are bigger than some point from S. Okay, so let's draw a picture because it's always a good start. Okay, so maybe I don't know, it could look something like that. There's S. Maybe T looks something like that. Okay, so these are two sets. The union of the two is the interval. We've chosen some point in S and some point in T. So here's our point S, here's our point T. So, okay, what's T0? T0 is all the points in T which are bigger than our S. Okay, so T0 is these points here. Okay. So the claim, the suggestion was to look at the infimum of T0. So, well, if this was a closed interval there, then the infimum of T0 would be there, it would be in the set. And so then, well, what's the distance between? Well, then, yeah, then there's certainly a point in S that's very close to that point, right? In fact, that point is actually in S. So here I've drawn them so they're overlapping. So maybe I've made my life a bit too easy. What about if it was like this? So that was an open, and that was closed, then it would still be the case. Oh, yeah. Okay, so it's all, drawing a picture helps all the time, so you should remember this lesson. Sorry for taking so long. So look, once we know that the infimum, okay, the infimum has to be in the interval, right? The infimum can't be less than A, okay, so it can't be strictly less than A, so the infimum is certainly in the interval. Okay, so the infimum is either in S or it's in T. Okay, so if the infimum is in T, okay, so here I've drawn it with a closed circle, so the infimum is in T, then by the continuity property of the reals, okay, there must be another point immediately below it. We can find other points arbitrarily close to that one, right? If the infimum is 0.5, we can find 0.4999, we can find 0.4999, we can find points arbitrarily close to that infimum. And those points must either be equal to S, okay, so there are two possibilities. Either those points below are equal to S, in which case they're in S, because they're in capital S, or there's some other point in capital S.
Oh yeah.
The other case is that the infimum is not in T naught. Okay. Well, if the infimum is not in T naught, then we could have had a picture where it was like this, say. Now the way around. These are open circles. It's a closed circle, so it has to be an S. Or we could have had a picture where S was on the threshold, but I don't know. It seems obvious now. Yeah. Okay, so let's do it formally. Okay, so C was our infimum. Okay, so case 1 was C is in T naught. And if you look at this is all X big, strictly bigger than S. Okay, so let's have two subcases. Case A, C equals S. Okay, if C equals S, then, well, S is in S. Okay, so we now have that the infimum of the set is something in S. Okay, therefore, for all epsilon greater than 0, there exists X in T naught such that this distance between S is less than X is less than S plus epsilon. Okay, because S is the infimum of this set T naught. Okay, so for any point, for any kind of upper bound, there must be a point that's so here's the upper bound. For S to be the infimum, there must be a point that's arbitrarily close to that upper bound. To that lower bound. I'm not being very clear. Yeah, so we've got this set T naught. T naught is a load of points. Okay. And here's the infimum at S. I'm saying, well, let's look at S plus epsilon. If there were no points in this interval, okay, then the infimum would be S, right? It would be S plus epsilon. So there has to be a point in that interval. Okay, so for any epsilon, there must exist some point there. Okay, so here we found this is what we're trying to prove. Okay, so here we found some points S and X. X was in T, which are a distance less than epsilon away from each other. Okay. So in that case, we're done. Case B is C not equal to S. Well, could that ever be true? Yeah, so here it's not true. In fact, I've done something a bit more. We don't even need this. Let's risk of slightly confusing you. Let's do things in the opposite order. Let's start with the case the infimum not in T naught. Okay, we still have the same two subcases. Either the infimum is equal to S or it isn't equal to S. Okay, if it's equal to S, then by the picture I showed you, okay, there must be some points less than epsilon. So we're fine there. If it's not equal to S, then we're in a picture like what we've got depicted here. Okay, here's the infimum is this point up here. It's not in T, and it's not equal to S. But still, even here, there must be points arbitrarily close, right? So let's look at the point C minus epsilon. Well, C minus epsilon is certainly less than C. Okay, so I think it's the same thing here as well. Yeah, okay, so C minus epsilon, well, it's certainly not in T naught for any epsilon. Okay. Because if it was in T naught, then the infimum of T naught would be C minus epsilon, not C. So if epsilon is small enough, then C minus epsilon is in our interval. Okay, so unless C was equal to A, the lower bound. This is so difficult. It's really obvious, isn't it, what we're trying to prove? Sorry, this is taking so long. Okay, so right, let's do even more cases. Okay, so case B was C not equal to S. Case I. So this is the case I is a subcase within case B, which is a subcase within case 1. Okay. C not equal to A, the lower bound of the interval. Okay? If C is not equal to the lower bound of the interval, then we can find some x in the interval between A and A and S, A and C. So this is the interval that includes A but doesn't include C. Okay.
I'm confused because
What?
aren't we talking about the interval now, which is C to D?
C to D?
Oh, I'm confused.
What's D?
I don't know. Aren't we looking at the interval that the function is on, not the interval that the? Oh, yeah, I'm confused myself.
Oh, well, I kind of forgot about what we were trying to prove originally.
Because you're saying it's greater than A, but aren't we talking about the interval that we're mapping onto?
Were we? I'd forgotten. Let's go back to where we were. I think you're right. Oh yeah, so these were subintervals of J, weren't they? No. No. S and T were adding up to I. Union of S and T was I, not J. So S union T is equal to I, which we said was A.
Okay.
Okay.
Sure.
So-
Okay. So.
15. What was it? Can you remember what we were looking at? I need to keep going.
No, 6.13 or something.
Well, it's fine, we So then the sum point. Okay, so we've got these three cases. There must be some point between A and C. Either this point X is in S or it's in T. Okay, so if X is in S, then and we C not equal to A, C minus, so for all epsilon greater than 0, for example, X and C minus epsilon comma C. Okay, so this is this picture here. For all, if this point isn't the lower bound, then we must be able to find points arbitrarily close to it below it. Okay, and these points must either be in S or in T. Okay, if they're in T, then they're a point X in T with X less or equal to S, because we know they're not in T naught. Okay, so there must be a point X in T with X less or equal to S, that means there's certainly a point in T naught that means to get our points S, so we're trying to find, in all cases we're trying to find 2 points S and T which are close together, arbitrarily close together. So in this case, what we have is that there are points to the left of our infimum. Okay, if these points to the left of our infimum were in T, then there'd be points bigger or equal to S. Okay, so we'd have a picture that looked like let me redraw the picture. So we had, so suppose here's our S, and here's V. Okay, so here's T. So here's T naught starts. Okay. So this is kind of the world we're in, right? If the points immediately to the left of the infimum are in T, they it might be that they're not. Could be that there's a hole in S, right? Could be that S has a point there and then nothing.
But aren't we saying that, I know the function of x is greater than
So here we have the case where we're talking about the case where the points immediately to the left of our infimum are in T, but then it must be the case that for a point arbitrarily close to S within T. Okay, so we're done. Let's just do this graphically because it just wastes time. So the other case is when these points immediately to the left of the infimum are in S, okay, but then it's like this again. Okay, if we can find a point distance epsilon below the infimum that's in S, and we know we can find a point in T which is distance epsilon above the infimum, okay, then we've got a bound on the distance between those 2 points again. So that kind of completes. Oh, and if it was the lower bound, yeah, it would go through. I can't be bothered to do this. It's quite tedious, but for lots of cases. That doesn't matter. So we've kind of done case 1 at this point. Okay, so case 2 is C. The infimum was in T0. Well, if the infimum is in T0, then S is a point in S that's arbitrarily close to T. You know, we can find a point in T0 that's within epsilon. So, take the infimum of T0, then yeah, okay. So we're two possibilities. Again, if the infimum of T0 is actually equal to S, then we have that S is both in T and in T0, so they're arbitrarily close. If infimum of T0 is not equal to S, then it means that we're kind of in a position where we have something what we had before, where S was over here and we've got a closed circle there. Okay, then if we look immediately to the left, there must be points. Yeah, so if the infimum isn't equal to S, right, then this must not be a constraint, if you like. Okay, so this is the constraint. So when you go below C, you must be in S, not T. Okay, so you can find points close. Yeah, let's cut our losses in this way. That's quite a tedious exercise. So going back to what we were actually trying to prove to start with, okay, we had this function f which was continuous on the interval I, and we wanted to show that the image of I was an interval. Okay, we defined these two sets, S and T, okay, and the union of S and T was the interval, and the obvious claim, which we kind of didn't prove very well, was that S and T contain points that are arbitrarily close to each other. So suppose we've got some point that's zero distance from T. Okay, so that means there's so we've got some point in S such that we can find points in T that are arbitrarily close to S. Then we can find a series of points in T that converge to S. Okay, that makes sense, it's obvious. So by continuity of F, that sequence of points must converge to F of S. Okay, so we had this sequence Tn tends to S, so F of Tn must tend to F of S because F is continuous. And then this is claiming but every element of T is bigger or equal to lambda. Okay, so F of the limit must be bigger or equal to lambda. Okay, so F of S must be bigger or equal to lambda. But then that means that S must be in T. So we have that F of S is less or equal to lambda, and we have that F of S is bigger or equal to lambda. So it must be the case that F of S equals lambda. So lambda, okay, so lambda is also in the image of F, which is what we wanted to prove, right? Okay, so apart from that the exercise thing, but we didn't really do very well. It wasn't actually that difficult, maybe I should. And let's stop there, because we're dead. My energy levels went down 2 hours ago. My brain stops working. Oh, you wanted some exercises, didn't you? So don't do any from here. So from limits, those are kind of obvious. There should be L'Hopital's rule somewhere, which is really important. But F of Y tends to L. Difficulties encountered in theory. Don't do that, don't do that. Don't do that. Let me just put it on my screen so I can. So somewhere there's an exercise that asks you to prove something important. Ah, okay, we haven't got to it yet. That's alright. So. Now, basically, I'm just giving them some exercises. It's hungry. I'm hungry, sorry. So where did we start today? We started with We haven't had any exercises on series, have
No.
we? So, where are the first exercises? Examples. This one looks fun. 626-2. So exercise 2 from 626. That one looks a bit difficult. And then have a go at these. Have a go at 5 as well.
Mhm.
Yeah, so it will be using the various tests, you know, comparison tests, ratio tests, etc., to see which of them work. Functions is obvious. There's nothing to do there. It's functions. Have a go at 8:15:3. And 6. That's a nice easy one. So 8:15:3 and 6.
Mhm.
It's kind of horrible. Yeah, that'll do.
Thank you.
Okay, sorry for overrunning and thanks as well. Is anyone in this room? Can I just leave my stuff?
Shall we go to 5 again?
Yeah. Okay.
Okay, see you later.
See you later. Sorry for killing you.
It's okay. Thank you, bye.
Okay, bye.
He's not in the UK.
He's in Nigeria.
I'm sure I met him last week.
Can't get a visa. I don't know who you met last week. But
He was sat in the other PhD office,
okay.
and I spoke to him.
You sure he wasn't someone starting in September or something? Could have been here for an interview.
Well, yeah, I suppose it's possible.
I don't know.
I think I made the assumption that he had just started, and nothing in the conversation made me
Okay.
think otherwise. But that's not to say, you know, because we talked a bit about the courses and.
Okay. Very strange. I'm sure you're right. But
Well,
maybe
find
he's
out
just
when I see
lying
him.
and he just wants to mess with us.
What's his name?
Faisal.
Yeah,
Faisal,
exactly.
Yeah, I don't.
He was on the Masters, right?
Yes, I think so.
So that thing that I failed to prove earlier,
Yeah.
was actually very easy.
It wasn't.
It was very easy.
It was.
I don't know if you thought about it. You know, I think what I was kind of outlining on the board was kind of half working, but I was hopelessly unclear as you guessed that. I'm very tired. But actually it's really easy. All you have to do, so remember we had S union T equals I, and the claim was that we want to prove that for all epsilon greater than 0 there exists S in S, T in T such that the S minus T is less than epsilon. Okay, that was what we wanted to prove. So for any epsilon we can find points in the two sets that are arbitrarily close. So the sensible thing to do to start with is to say, well, suppose that, so there are two cases. Case 1, this is the idiot's case, S intersection T not equals the empty set. Okay, if S and T intersect, okay, then that means there exists some point X in the intersection of S and T. Okay, so therefore X is in S and X is in T, and you know X minus X is equal to 0, which is less than epsilon. Okay, so it's very easy in that case. There's nothing to do. The other case, then they don't intersect. Okay, and then it's a lot clearer why their hint helped. So the hint said.
But they can't intersect, can they? Because
Yeah, they can.
can they? Because isn't that just a set of x for which f of x is less than lambda and f of x which is greater than lambda? But x is only
less or equal to, greater or equal to. So they can intersect. Okay.
So it will be just L or...
No, so if they intersect, it's this case. If they don't intersect, we have this case. And we defined this T naught, which was the set X. So this is from the hint, X in T, such that... So we fix some S less than T. And then we define T naught to be this set X in T, X greater than S. Okay, then... And let's see, this is non-empty, it's bounded below. We did show that before. Let C be the infimum of T0. So this is well defined because it's non-empty and bounded below. So if C is in T, then this is when I go wrong. If C is in T, then you know what we have. We've got this set. So C is in T. Every element of T0 is bigger than S. Okay, so it's certainly the case that C is bigger or equal to S. Okay, possibly C could be equal to S. Well, could C be equal to S? Well, if C is in T, then because S and T don't intersect anywhere, C is not in S.
Yeah.
Okay? Therefore, if C is bigger or equal to S and C is not in capital S and S is in capital S, then C can't be equal to S. Okay, so then C is strictly greater than S. Okay, so now let's look at the interval between S and C. Well, this interval will every point in this interval is below C. C is the infimum of T0. Okay, so every point in this interval is certainly not in T0. So all we and in fact it's going to be the claim is that this is going to be in S, And why is that the case? Well, suppose, okay, so this is our claim that this interval, open interval from S to C is a subset of S. So suppose we had X in this interval, okay, then what would we have? Well, X would be greater than S, okay, but X is also greater than C, which means that X is not in T0. Well, X is greater than S, so it satisfies this condition to be in T0, so this condition to be in T0 must be false. Okay, so it can't be the case that X is in T, therefore X must be in S. So any element of this set, X, the open interval from S to C, is in S. So, so we can find points arbitrarily close to this right upper limit, which are in S. Okay, and C is in T. Okay, so we can find for any epsilon, epsilon greater than 0, there exists there exists some point X in S, okay, with X less than C. X, yeah, what am I saying? X with X in the interval from C minus epsilon up to C. Okay. Yeah, this open interval is all in S. Okay, so we can find points arbitrarily close to the right hand side. Okay, so we can find points arbitrarily close in S to this right hand side, but C is in T. Okay, so we found 2 points arbitrarily close, one in S, one in T. So that's the case if C is in T. If C is not in T, okay, then C is in S, because the two sets are disjoint. Okay, so C is the infimum of this set, and it's in S. So C must be arbitrarily close to points in T0. You know, by the definition of the infimum, we can, for any epsilon, we can find a point arbitrarily close to C in that set. So, okay, so well, it wasn't actually that difficult, but yeah, just taking out this case first and then intersecting made everything so much easier. And somehow,
I find these proofs are usually really easy and straightforward when you know them.
yeah.
Trying to write them out and work through them logically can be quite difficult.
Yeah, so a lot of it is practice. You learn the tricks, and then things are easier.
Is this what you did in your undergrad?
So this textbook is first year, first term undergrad.
Really?
Yeah. So
It's learning a language really.
Yeah.
yeah.
It's not like difficult.
Okay, so the exercises. Which ones did you ever go at? Did you go over anything else? What were you stuck with?
I did some of them.
So we started with those ones on series, didn't we?
Mm.
So what did you have a go at?
So page 62, it should be 60, yeah, 62.
Exercise 2.
I did that,
Question 2.
yeah. You can have a look, because I think somewhere, I think I missed something. I don't explain very well.
So we've got these two sequences,
Which
A
are
over.
positive, right?
Okay.
Positive terms, and we have that. So we need to prove that if either both converge or both they
don't
converge.
actually.
So I just, if if they are positive, it means that we can take absolute, right?
Yeah, they're the same.
And we have that which implies this.
Yeah, you're told. Yeah, sure.
And I was just
well,
trying to
for-
find
for
a
sufficiently-
relationship.
For sufficiently large n. Yeah.
Oh, yeah.
Yeah.
I was trying to find a relationship between A and Bn in order to use this theorem. This comparison, no.
Mhm.
Yeah, this comparison test theorem.
Yeah. Okay.
But I don't know if I took the right one because I did what we did here, 617 theorem, where we had.
But we don't know that Bn is a convergent series. That's the problem.
No, but if we assume that this
then
is
if that converges, then An converges
Yeah.
too by the comparison test.
and the other way around, but I was just trying to prove that we have a relationship here from this.
Yeah. So I think this is. So and does it tell you that L is less than 1 in the exercise?
I think it
Well,
says
Well, L is not
no
zero.
zero, yeah.
Okay.
So I
So
don't know
certainly
if that's right.
Yeah. So if L is less than 1, then yeah. So the limit is less than 1, then we can certainly find a point beyond which An is always less than Bn. So yeah, if Bn converged, An would converge too. If L, yeah, I think that's probably what it wanted you to do. Is reversion of the comparison test for divergence? Then the series convert. Ratio test. Yeah, I think that's probably what it wanted you to do.
So for this will be for L less than.
Yeah, that only
1.
works with L less than 1.
Okay. And then I just took it from the comparison test
Yeah.
for these 3 cases.
So 1
So
over
this is
1 over 2n is what did you say that was less than? What did you bound it by? Half 1 over n. Yeah, okay. So so the comparison test we had was for convergence. So can you do it for divergence? Say something about. Oh, I know what you. So.
Which question are you discussing?
So this is 626, question 2. So we had. So they helpfully, there was a bit of a clue there in saying that L was non-zero. Okay, so we had that the An over Bn tends to L as n goes to infinity. So by what we had about ratios, it's also the case that Bn over An goes to 1 over L as n goes to infinity. Because L's not equal to 0. So you know, what you did was right. You said that An. So if we take, if L is less than 1, then we can set epsilon equal to what I did before, 1 minus L over 2. Then we have that An over Bn minus L is less than 1 minus L over 2, which, you know, you do the manipulations, tells you An over Bn is certainly less than 1. Okay, so An is less than Bn. then on the other case, if L is bigger than 1, then we can take epsilon is 1 minus 1 over L. It's 1 over L over 2. And we know that Bn over 4. Yeah. So I missed it. So resist n in n such that for all little n bigger or equal to big N, etc. And the same thing there. Bn over an minus 1 over L is less than 1 minus 1 over L. 1 over L over 2, which implies in this case that Bn is less than An. So if L is less than 1, then An is less than Bn for large N, which is what you had. If L is bigger than 1, then Bn is less than An for large N. Do we know L is positive? No.
No, it doesn't.
No. So if L...
Well, we do actually, because we know that they're A and B are both positive.
Yeah, we do, okay. So we've got two cases. If L is bigger than 1, then An is always less than Bn, so yeah, by the comparison test, if the series Bn converges, then the series An converges. If L is bigger than 1, then yeah. So you had it right, basically. It's just kind of know that assumption. Yeah. And then these examples, you know, you would think that it would be using what we just proved, wouldn't we? Wouldn't it? But,
yeah, just for the first one, I took it from theorem 6.
yeah.
I didn't use the comparison test. Yeah, and for the second and the third, I used the comparison test.
Okay. So yeah, so I guess what the question, I think you probably did it right, but what the question wanted us to do was to use what we just proved. Okay, so let's see if we can do it using what we just proved. So all you have to do is, because the comparison test is for convergence, not for divergence. You know, if Bn diverges, it doesn't necessarily mean that An diverges. Okay, so you've got An is less or equal to Bn.
Yeah.
We're looking at the sum of the Ans and the sum of the Bns.
Yeah.
Well, this thing can be equal to infinity.
Yeah.
This can diverge, but this can still be finite. Okay, so if this converges, then this converges, but it's not the case that if this diverges, then this diverges. Although, yeah, I suppose it is the case that if this diverges, then that diverges.
Yeah.
Okay, because if that converged, then that would converge. Okay, so maybe that's what you did. So 1 over 2n. Okay, so to prove divergence, you need. There's always one sequence here, but we know one sequence, but we don't know how it behaves. Like, so we know how 1 over n behaves. We don't know how 1 over 2n behaves, for example. So you want to prove divergence. You want the series that you know to be this one. Okay. So you want to set an is 1 over n, and bn is, well, so yeah, I think you did it a clever way, taking a half out the front. So if you take bn is 1 over n as well, like you did, okay, then we have sum of 1 over 2n is half sum 1 over n. So it kind of diverges by comparison with itself.
Yeah.
Or if we do it using what we just proved, Okay, so what we just proved was about these ratios. So we can take an is, it doesn't really matter now which one we call an, which one we call bn. Take an is 1 over 2n, and bn is 1 over 2n. Then an over bn is equal to 2. This tends to some limit as n goes to infinity, so either they both converge or they both diverge. We know this diverges, therefore this diverges. So similarly for the next one, we take an 1 over n again, we take bn is 1 over 2n minus 1, is that right? Okay, then an over bn is 1 over n over 1 over 2n minus 1, which is 2n minus 1 over n, okay, which is 2 minus 1 over n, okay, which goes to 2 as n goes to infinity. So this thing diverges,
Yeah.
this thing diverges, so this thing diverges as well. Okay,
Mhm.
by what we proved before. And then the last one was 2 over n squared plus 3.
Just an diverges, and the second one goes to 2 as n goes to infinity. Right?
So an, we defined an as this,
Mhm,
bn
mhm,
is what
mhm.
an is what we know here, bn is what we're interested in. We look at an divided by bn, so we're looking at the ratio,
Yeah.
just like in the question. And we showed that the ratio goes to 2 as n goes to infinity. Okay, so therefore by the question, if an converges, then bn converges, if an diverges, then bn diverges. We know that an diverges, okay, so
Okay.
therefore bn diverges as well. So this is just kind of another form of the comparison test,
Okay,
if you
mhm.
like. Slightly more general from the normal comparison test. And the last one was, we take an is 1 over n squared, bn is 2 over n squared plus 3, is it right? Okay, then an over bn is 2 is n squared plus 3 divided by 2n squared, which goes to a half, as n goes to infinity. Therefore, if this converges and this converges, we know that 1 over n squared, the series converges, so therefore this series converges as well.
Okay.
What else did you have a go at?
Could we do some of exercise 5? I didn't know how to prove that. Exercise 5. For
Okay.
example, if we can do the first one and then.
Okay. Good. These are horrible, aren't they? Did you have a look at the answers?
Yeah, it says if you go with the ratio.
Ratio test.
Yeah, but
okay,
I
well, let's
don't know.
have a go with that. So the series we have an is n factorial. What is it? N factorial squared over 2n factorial. Okay, so an plus 1 divided by an, that's what we want for the ratio test. But n factorial squared, oh, sorry. It's n plus 1 factorial all squared divided by 2n plus 2 factorial all divided by, well, we had to start with n factorial squared divided by 2n factorial. Here's a new pen. Okay. So this is just substituting n.
Okay. I see.
Yeah, an plus 1 over an. Well, let's make it look more like a fraction. So this is n plus 1 factorial all squared times 2n factorial all divided by 2n plus 2 factorial times n factorial squared. So, well, what's n plus 1 factorial divided by n factorial?
N plus 1.
Yep.
Yeah.
So n plus 1 factorial squared divided by n factorial squared.
Is N plus 1 squared.
Okay, so we have an n plus 1 squared. So that's taking care of these two terms. And then we have 2n factorial divided by 2n plus 2 factorial.
Two? No.
1. Yeah, it's just n over n plus 2. N factorial over n plus 1 factorial.
No.
And 2n, right? Maybe n times 2.
So we get, so think, I've started writing now. This is the product of all numbers up to 2n plus 2. This is the product of all numbers up to 2n. Okay, so the extra terms that this one has that this one doesn't have is this one has 2n plus
Yes.
1 and then it has 2n plus 2.
Yeah.
So we just have these two extra terms on the bottom. 2n plus 2 times 2n plus 1. Okay, so
I don't follow that. Because 2n plus 2 is...
okay, so let's do an example. Let's do n is 2 because the numbers get bigger, too big otherwise. Yeah, n is 2. Okay, so 2n factorial is 4 factorial, which is 1.2.3.4. 2n plus 2, this is in brackets, 2n plus 2 all factorial is, what are we on, 6 factorial, which is 1.2.3.4.5.6. Okay, so the ratio 2n factorial divided by 2n plus 2 factorial is 1 divided by 5 times 6, which is 1 over 30.
Okay.
Does that make it clear of the example?
Yeah.
So, you know, all these terms cancel out, we're just left with the last two terms. The 2n plus 1 and 2n plus 2 terms. Okay, so for the ratio test, we need to know whether this tends to something above or below 1. Well, looks like it tends to something below 1, doesn't it? So this is certainly less than n plus 1 squared over 2n plus 2. Oh no, that wasn't right. Okay, so how we think this probably converges to, you know, if it wasn't for the constants, just ignore the constants for a second. So we'd have n squared over 2n times 2n, so n squared over 4n squared. We think that converges to a quarter. So a reasonable guess would be that this converges to a quarter, right? When n is large, the constants aren't going to matter. So, well, we can we prove that quickly? Well, so let's just do it quickly. N plus 1 squared over 2n plus 2 times 2n plus 1 minus a quarter. Okay, that's equal to I know. So we can rewrite. Do you remember partial fractions? Okay, if you have an expression where you've got factors on the bottom, you can always write it, or I think this is right, sometimes I don't know. We can, so here's what we have to start with, 2n plus 2 times 2n plus 1. And I'm going to guess that that is equal to a over 2n plus 2 plus b over 2n plus 1 plus c.
Oh my goodness, I haven't seen this in school.
Yeah, it's a long time ago. But I think that's what you do in school, isn't it?
It's something like that.
It's something like
definitely.
that. Let's hope it works.
Oh yeah.
Just a second. Partial fractions. Let's just check this is right before I make a mistake. Okay, so this is our guess, and we want to find these missing coefficients, a, b, and c. Okay. The Wikipedia page isn't very clear. Examples. Here we go. This is what we want. Factor of a denominator. Yeah, it's exactly right. Okay, so this is our guess. So let's multiply both sides by 2n plus 2 and 2n plus 1. Okay, so we have n plus 1 all squared is equal to a times 2n plus 1 plus b times 2n plus 2 plus c times 2n plus 1 2n plus 2. Okay, so n plus 1 squared is n squared plus 2n plus 1. Okay, put the equals there. So if we kind of we want to match the n squared terms and the n terms. Okay, so we get A, B, and C are just going to be constants. So A, B, and C aren't going to be functions of n. Okay, so the only way we can get an n squared term is from C. Okay, so it must be the case that 1 is equal to the n squared term from C, which is 4n squared. Which is
4c.
Yeah, 4c. So here we have 2n times 2n, so that gives 4n squared, and we've got a c in the front, so we've got 4c n squared.
Yeah.
So it must be the case that 1 is 4c. So c must be equal to a quarter. Okay, so let's plug that in. So this is now a quarter. And so when we multiply out this brackets, then we get, so it would have been 4n squared, now it's just n squared. We get plus 2n plus 4n. Okay, so in total we get 6 plus 6n divided by 4, so 6 over 4n, which is 3 over 2. Okay, plus 3 over 2n. And then we get 2 divided by 4, which is a half. Okay, so we've done the n squared terms. Now let's look at the n terms. So we have, on the left hand side we have 2, on the right hand side we have 2a plus 2b plus 3 over 2. And the constant terms we have 1 on the left hand side, then we have a, then we have 2b, then we have a half, sometimes as I've done this. Here we've got 2b here, we've got 2b there. The easiest thing to do is just to subtract this equation from that equation. Okay, so we do this equation minus that equation. So that gives us 1 is equal to a plus 3 over 2 minus a half, which is 1. Okay, so a is equal to 0. Is that going to work?
I'm confused how you'll end up with a quarter. That's for sure.
A quarter?
Well, that's what you put over there on the right hand side of the whiteboard, isn't it? You gave the answer away.
Oh, that was a guess.
Oh, right. That was quite a good guess. Where we're heading. Yeah, this can work, can't it?
Is it? Can A is 0 work? So if A is 0, what's B?
Something.
Okay. So we think this means, I haven't made a mistake, have I? So this means A is 0.
Probably
So-
have.
I probably have, yeah. So then we have 1 is 2b plus a half. Okay, so 2b is equal to a half. Okay, so b is equal to a quarter. And let's just check that works in the first equation. We've got 2 is, so this is 0, so 2 times b is a half. Half plus 3 over 2 is 2, which is, okay, so this works. Okay, so here we have a partial fraction. C is equal to a quarter. B was equal to a quarter as well, and A was equal to 0, so that term just disappeared. In fact, it was obvious that one term was going to disappear, wasn't it? So we could have seen... I'm such an idiot sometimes, I'm sorry. So this thing, 2n plus 2, is just equal to 2 times n plus 1.
Yeah.
So we could have done that and then cancelled out. We still would have needed to do a partial fraction, but it would have been an easier one. Okay, I'm a bit stupid sometimes.
Okay, we remember partial.
Partial fractions, it's useful. Okay, so as n goes to infinity, this goes to infinity, this bit disappears, so the fraction goes to a quarter. And I guess was right. Okay, and remember we were trying to use the ratio test. A quarter is less than 1, therefore this converges.
Hang on. The whole thing doesn't go to a quarter, because that's quarter over 2n plus 1 plus a quarter.
Well, this goes to 0, this bit disappears.
Oh, yeah.
I have to trust my guesses.
Yeah, that's a good guess.
Well, it's kind of, it was a sensible guess because the constants normally don't matter. Okay, so if you just ignore all the constants,
Yeah.
you've got n squared over 4n squared, which is clearly going to go to a quarter. So that's where my guess came from. Okay, so this is less than 1, so the ratio test says that this series converges. Oh, sorry, did you want to?
No, yeah, I'm
No.
fine.
And I expect the other parts of 6 were similar, were they? It'll be the same technique in each case, I think. What else did you have a go at?
The next one, which was, let me see. Okay. So I did exercise 3 from page 80.
Okay.
I think it was easy.
Let f be defined for all x except x is naught, that one.
Yeah, but we can do, you can see what I
Okay,
did,
I'll
and
have a look
if
at
we
it.
can do exercise 5, which was more complicated, this one.
Mm-hmm. Excellent. Okay, okay. So it just simplifies down.
Yeah,
Okay, that is.
I
Does
think
simplify.
it was,
It does simplify a lot.
So when I did that, I was, maybe I didn't understand something.
Looks fine. So f of x is 2 plus x. Prove that f of x tends to 2 is, that's clear. even though f of naught is not defined. Yeah.
Then we can do
yeah.
exercise 5, which was really complicated.
Okay. This will write at naught. Hint used for sandwich theorem. And examine exercise 3.112. Did you look at what did that say? Okay, so 3.112 was that sum k is naught to n, x to the k is 1 minus x to the n plus 1 over 1 minus x. Remind me what exercise, what page, we're on 80 or something?
80, yes.
Yeah.
5.
Okay, use the sandwich theorem. One over L. N is just some constant. Yeah, it's probably not too bad. Okay, so let's choose a point x star. Let x star in in 0 to infinity. And let's let epsilon greater than 0. Okay, what we want to prove is that okay, so we want to prove that there exists delta greater than 0 such that for all x in x star, x star minus delta, x star plus delta, f, what was it, x to the 1 over n? Absolute value of x to the 1 over n minus sorry. I should do it the way I did it before. So f of x star is what x star to the power of 1 over n. That's the epsilon. So that's what we want. That's what we want. Should we just have a look at the answers rather than? You got the answers there?
Yeah,
Rather than me,
but I didn't understand. So, yeah, 3, 5.
It says 3.116.
Yeah, which is here, yeah, I think.
Oh, okay. I thought it said 3.112. There's naught. Okay. Okay, yeah, maybe it was a bad question to ask you. Did you spend a long time on it?
A bit. I tried to follow what we did when we need to show that f. We did something in the morning.
Yeah.
And I try to follow that, but it didn't work.
Yeah. So the answers say that this exercise 3.116 is precisely about terms of reform x to the 1. So if you look at what we're trying to prove, we've got a difference in terms to the power of 1 over n. So we've got 2 points x and x star. And this thing from exercise 6 is giving us 2 bounds on terms like this. Okay. So this is saying it's less or equal to yx to the 1 over n. One of these x and y belong to the interval x, y. Okay, so we could do it in fact. Let's take this as given. Okay, I'm not going to prove that, but let's prove it a slightly different way to the way they proved it. Maybe this will be clearer. X and y belong to the interval x, y. So let's take x star minus delta as our capital X and x star plus delta as our capital Y. Then it's certainly the case that x and x star both belong to the interval square brackets x, square brackets y. Okay, so x star are both in this interval x, y. Okay, so then this claim says that that n x y x to the 1 over n minus x star to the 1 over n is less or equal to y times x to the power of 1 over n x minus x star. No, let's do. Sorry, I'm going to change my mind a bit. Sorry. So this is a statement of what we had. I'm going to change the definition of x and y. Let's take x equal to x star over 2 and y equal to 2 times x star. Okay, then it's certainly still the case that x and x star are in the interval. Okay, as long as yeah, we can always choose a delta such that this thing x and x star will be in that interval with that particular delta. But so because this is what we're trying to prove, remember. So we don't currently know the value of delta. We're trying to get to a value of delta. Okay, so let's take x and y like this, which aren't a function of delta because we don't know delta yet. Okay. So then if we plug into this inequality, we have that x times y is this and this cancel, so it's x star squared and x star squared times x to the 1 over n minus x star to the 1 over n is less or equal to y. So y is 2x star times x star over 2 all to the power of 1 over n. Okay, so if we divide through by this thing, we get 2 over x star over 2 to the power of 1 over n Well, that's just x star over 2 to the power of 1 over n minus 1 times x minus x star.
Divided by n, no?
So y divided by n? This n has come... Oh yeah, sorry, 1 over n. Yeah. So this is what we're trying to bound. This is the difference between f of x and f of the limit. This is what we can bound. Okay? So remember, we have to prove that there's just some delta for which, if x is in that region, then this is true.
Mm-hmm.
So we want this thing to be less than epsilon. Well, when is this going to be less than epsilon? It's going to be less than epsilon providing x minus x star is less than epsilon over the n epsilon times x star over 2 to the power of 1 minus 1 over n. Okay, I've just divided through by this. I flipped the sign of that, so it's now 1 minus 1 over n.
Okay. Mm-hmm.
Yeah. So this is less than epsilon if and only if. This is an if and only if. That. So if we take delta to be this thing, so we can define delta to be this thing. So we're kind of working backwards in this proof, but if we define delta to be this thing, we know that if x minus x star is less than delta, then x for 1 over n minus x star to 1 over n is less than epsilon. Okay, so this gives us the continuity.
Okay.
And the reason you can see here why you have to treat the endpoints differently. Okay, because we took x star over 2 and 2 times x star. But yeah, it would have been hard to do this if I hadn't been told, that this was the inequality I needed. I wouldn't have known what to do. So I don't know why the hint pointed you to 3.1 part 2 rather than 3.1 part 6, which was actually what you needed.
Okay, thank you.
Is there anything